Somewhere in our galaxy, about 12,000 light years from where you are sitting right now, a star very much like our sun began to brighten. It happened without warning. Over the span of just 10 days, this ordinary middle-aged star flared to roughly 100 times its normal brightness, throwing out a burst of light and a slow, expanding cloud of glowing dust. Astronomers on Earth caught it in the act, and when they pieced together what they were actually looking at, the conclusion was so unsettling that one of them said it out loud, plainly, to anyone who would listen. They were not watching a nova. They were not watching a collision between two stars. They were watching a star swallow one of its own planets. A whole world gone, consumed by the same fire that once warmed it. And the lead scientist put it in words nobody on this planet wanted to hear. He said they were seeing the future of the Earth. We will come back to that dying star. But first, you have to understand what they were really looking at, because the same thing is going to happen here. There is a fire above your head that has been burning for an estimated 4.5 billion years. It does not flicker, it does not rest. Every single second, in the core of our sun, 600 million tons of hydrogen are crushed together and transformed, and 4 million tons of that simply vanish, converted into pure energy and flung out into space as light. 4 million tons of matter destroyed every second. That is the weight of a small mountain, erased every time your heart beats, and it has been doing this, without pause, for billions of years. That light is the reason you exist. Every blade of grass, every ocean current, every breath drawn by every living thing on this world is paid for in that vanished mass. The sun is not a comforting presence in the sky. It is a controlled, self-sustaining explosion the size of 1 million Earths, held together by nothing but its own crushing gravity. And the only reason it has not torn itself apart is that gravity and fire are locked in a perfect silent war at its center. But here is the part that should keep you awake. That war has a winner, and it is not the one keeping you alive. The sun is not eternal, it is not even permanent. It is a furnace burning through a finite supply of fuel, and the day that fuel runs out is already written into the laws of physics. We can calculate it. We have calculated it. And the answer is not a vague maybe somewhere in the unimaginable distance. The answer is a sequence of specific, violent stages, each one more extreme than the last, ending in something most people have never been told. The sun will not simply fade away like a candle. Before it dies, it will swell into a monster. It will turn red and bloated and grow until it reaches out across the inner solar system. It will boil Earth's oceans into space. It will very likely engulf this entire planet, melting the ground you are standing on into vapor. And then, after that violence, it will collapse into something so dense that a single spoonful of it would weigh as much as an elephant. This is not science fiction. This is the verified, peer-reviewed scientific forecast for our own star, built from more than a century of observation and from watching countless other stars die exactly this way across the galaxy. By the end of tonight, you're going to understand how the sun actually works, why its death is not a possibility, but a certainty, and what each terrifying stage of that death will look like. You're going to learn why life on Earth has a deadline far, far sooner than the sun's own. A deadline measured not in the billions of years most people assume, but in something much closer. You're going to meet the scientists who first realized our star was doomed, the ones who were told their ideas were impossible, and the ones who lived to be proven right. And you're going to discover the single strangest fact in this entire story. The reason the death of the sun is also, in a way, the reason you are alive at all. There is one number in this story that will change how you look at the sky. We will get to it, but not yet. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. For now, look up, picture that quiet, golden light, and understand that you are looking at a clock. A clock that has been counting down since long before the first ocean formed, and that will keep counting long after the last one is gone. The sun is dying. It has always been dying. The only question worth asking is what its death will look like, and whether anything we build will be there to witness it. Now, let's begin. To understand how the sun will die, you first have to understand a question that haunted the greatest minds of the 19th century. It is a question so simple a child could ask it, and yet for decades it broke every scientist who tried to answer it. The question was this: what, exactly, makes the sun shine? It sounds almost too obvious to matter. The sun is hot. The sun gives off light. Of course it does. But press a little harder and the whole thing falls apart. Light is energy. Energy has to come from somewhere. Nothing burns forever. A campfire dies in a night, a coal fire in a day. So what was feeding this fire in the sky, and how long could it possibly last? In the middle of the 1800s, two of the most brilliant physicists alive, Lord Kelvin in Britain and Hermann von Helmholtz in Germany, set out to answer it. They were not careless thinkers. Kelvin was the man who helped define the very meaning of temperature, and they reasoned it out carefully. The sun could not be a chemical fire, they realized, because if the entire sun were made of the finest coal and set alight, it would burn out completely in just a few thousand years. The sun was clearly far older than that, so they reached for the most powerful force they knew: gravity. Their idea was elegant. The sun, they proposed, was slowly shrinking under its own enormous weight, and as it contracted, that gravitational collapse released heat, the same way a falling object speeds up and gains energy. A sun that was forever falling inward upon itself could glow for a very long time. They did the math, and the math gave them a number. By their calculation, the sun could shine for somewhere around 20 to 30 million years, no more. For a while, that felt like a triumph. 20 million years is an enormous span. But then, the rest of science walked into the room and called it a lie. The geologists had been reading the rocks, the slow grinding of rivers, the laying down of sediment, the patient carving of canyons. These processes left records, and those records did not speak of 20 million years. They spoke of hundreds of millions, of vast and unhurried ages of the Earth. And then came an even louder objection. The naturalists studying the living world insisted that the slow, patient changes they saw in fossils required oceans of time, far more than Kelvin's sun could provide. There was a brutal contradiction at the heart of science. The rocks and the living world demanded an ancient sun. The best physics of the age insisted on a young one. Something was wrong with our assumptions. Somebody had to be making a terrible mistake, and nobody could find it. The mistake, it turned out, was that the answer simply had not been discovered yet. The fuel powering the sun was not chemistry. It was not gravity. It was a force nobody in Kelvin's lifetime even knew existed, a force hidden inside the atom itself. The first clue arrived at the very end of the 19th century, when Henri Becquerel left some uranium salts in a drawer with a photographic plate and discovered, to his astonishment, that the plate had been exposed by an invisible energy pouring out of the rock for no apparent reason. Radioactivity, matter, it seemed, contained a hidden reservoir of energy locked deep inside it, leaking out on its own. Marie and Pierre Curie chased that thread into the heart of the atom, and then, in 1905, a young patent clerk named Albert Einstein wrote down a single short equation that would rewrite the story of the sun forever. Energy equals mass times the speed of light squared. In plain words, mass and energy are the same thing in two different costumes. And because the speed of light is an almost unthinkably large number, that equation hid a secret with terrifying implications. A tiny amount of mass, if you could somehow convert it directly into energy, would release a staggering, almost limitless flood of power. Suddenly there was a candidate for the sun's fuel that nobody had dared imagine. The sun was not burning. The sun was converting itself, gram by gram, into light. The man who first dared to say it out loud was a quiet, formidable British astronomer named Arthur Eddington. In the 1920s, Eddington argued that deep in the core of the sun, under pressures and temperatures beyond anything on Earth, hydrogen atoms were being fused together into helium, and that in this fusion, a sliver of mass was being lost and released as pure energy, exactly as Einstein's equation allowed. His colleagues told him it was impossible. The temperatures in the sun, they argued, were far too low for atoms to overcome their natural repulsion and slam together. Eddington's reply has echoed through physics ever since. He told them, in effect, to go and find a hotter place. There was no hotter place. The sun would have to do. Eddington was right, and the universe would soon prove it. But before that could happen, someone had to figure out what the sun was actually made of. And the answer to that came from a young woman whose discovery was so radical that the most respected astronomer in America told her she was simply wrong. Her name was Cecilia Payne. In 1925, working on her doctoral thesis at Harvard, she analysed the light of the stars with a care and a mathematical rigour that nobody had matched. When starlight is spread into a rainbow, it carries dark lines, fingerprints left by the elements inside the star. Payne read those fingerprints, and they told her something nobody expected. The stars, including our sun, were not made of the same stuff as the Earth. They were overwhelmingly made of the two lightest elements that exist, hydrogen and helium. The sun was a vast ball of the simplest material in the cosmos, and the heavy elements that make up the ground beneath your feet were barely a trace. When she submitted this conclusion, the leading astronomer of the day, Henry Norris Russell, pressured her to soften it, to call her own result almost certainly not real. The idea that the sun was mostly hydrogen contradicted everything they thought they knew. So she added a line walking it back, and then, a few years later, Russell did the calculation himself, arrived at exactly the same answer, and the field finally accepted it. The thesis is now remembered as one of the most brilliant ever written in astronomy. Cecilia Payne had handed the world the fuel, an ocean of hydrogen, billions of times more than any chemical fire could ever need. Now the pieces were on the table, a core hot enough and dense enough to fuse atoms, an equation showing that fusion releases enormous energy, and an almost endless supply of hydrogen to burn. All that remained was to figure out exactly how the fusion worked, and that final piece was placed by a German-born physicist named Hans Bethe, who in 1939 worked out the precise nuclear reactions that power stars like the Sun. He traced the step-by-step path by which 4 hydrogen nuclei are forged into one helium nucleus, releasing energy at every stage. It was such a complete and beautiful solution that Bethe would later receive the highest prize in science for it. The mystery that had broken Kelvin and Helmholtz was finally solved. The sun shines because, in its heart, it is slowly turning hydrogen into helium and light, destroying a fraction of its own mass with every reaction. And that single answer carried within it a death sentence. Because if the sun runs on a finite supply of hydrogen, and it does, then the sun must, one day, run out. The very discovery that explained why the sun could last billions of years also proved, beyond any argument, that it could not last forever. The clock was real, now they could read it. But there is a deeper layer to this story, and it is stranger than the death sentence itself. Because once physicists understood what was supposed to be happening in the core of the sun, they ran the numbers, and the numbers said something alarming. By the strict rules of classical physics, the sun should not be able to shine at all. Here is the problem. Fusion means forcing 2 atomic nuclei to touch, but every atomic nucleus carries a positive electric charge, and like charges repel each other with ferocious strength. The closer 2 nuclei get, the harder they are pushed apart. To slam them together hard enough to fuse, you need to overcome that repulsion, and that requires staggering energy, which, in a star, means staggering temperature. When physicists calculated how hot the core would need to be for protons to collide hard enough to fuse, they got a number far, far higher than the 15 million degrees actually found inside the sun. The center of the sun, by this reasoning, is simply too cold. The protons in there are moving fast, but nowhere near fast enough. They should approach each other, feel that wall of repulsion, and bounce away every single time. The sun should be dark. The resolution came from the bizarre new physics of the very small. In the 1920s, a Russian physicist named George Gamow realized that the world of atoms does not obey the tidy rules we expect. A proton is not a hard little ball with a definite position. It is a smear of probability, a wave of possibility. And a wave can do something a ball cannot. It can leak through a barrier it does not have the energy to climb over. This is called quantum tunneling, and it sounds like magic, but it is one of the most thoroughly tested phenomena in all of science. Every so often, a proton that should bounce off the wall of repulsion instead simply appears on the other side of it, as if the wall were never there, and fuses. The sun shines on a loophole in the laws of physics. Without quantum tunneling, the sky would be black and you would not exist. And it is rarer still than even that. There is a second bottleneck, and it is the most important fact about why we are alive. When two protons finally do tunnel close enough to fuse, they cannot simply stick together, because two protons alone cannot form a stable nucleus. For the reaction to proceed, one of those protons must, in the same instant, transform into a neutron, and that transformation is governed by the weakest force in nature, a force so feeble that the event almost never happens. A given proton in the core of the sun can wait, on average, billions of years before it successfully fuses. Billions of years. The core of the sun is not a roaring inferno burning through its fuel as fast as it can. It is the slowest, most reluctant, most inefficient nuclear reactor imaginable. And that is precisely why we are here. If fusion in the sun were efficient, the sun would have exploded its fuel in a geological eye blink and gone dark long ago. Because fusion is so painfully, absurdly slow, the sun can burn steadily for 10 billion years, holding still just long enough for oceans to form, for continents to drift, for life to take hold. We owe our entire existence to the fact that our star is, by any reasonable standard, terrible at its job. So what keeps this slow, vast furnace from either collapsing or blowing apart? The answer is a war, a perfect silent stalemate that has held for billions of years. On one side stands gravity, the weight of all that mass pulling inward, trying without rest to crush the sun into a single point. On the other side stands the outward pressure of all that heat and light pouring up from the fusing core, pushing outward, trying to blow the star apart. For the entire main sequence life of a star, these two forces are locked in an exact trembling balance. Physicists call it hydrostatic equilibrium, but the plain truth of it is more dramatic than the name. Every star you have ever seen is a bomb and an implosion happening at the same time, frozen in a drawer. And this balance is self-correcting, like a thermostat. If the core fuses a little too fast, the extra heat makes it expand and cool, which slows the fusion back down. If it fuses a little too slow, gravity squeezes it tighter and hotter, which speeds the fusion back up. This is the great secret of the sun's long stability. It regulates itself. It is a machine that keeps its own hand steady. Hold on to this idea because it matters enormously for everything that comes later. The day this thermostat finally breaks, the day fusion outruns gravity's ability to hold the line, is the day the sun stops being a quiet star and becomes a monster. We will come back to that broken thermostat. It is the engine of the sun's death. There is one more thing the early physicists wanted, and it seemed impossible to ever get. They wanted to look inside the sun. Everything we have described happens in the core, buried under hundreds of thousands of kilometers of blinding plasma. No telescope can see through that. The light from the surface tells us about the surface, not the heart. For decades, the fusion happening in the center was a theory, beautiful, consistent, but unconfirmed by direct sight. How could you ever prove what was happening in a place no light could ever escape? The answer turned out to be ghosts. Every fusion reaction in the core does not only release light, it also releases a particle so faint, so unwilling to interact with ordinary matter, that it passes straight through the entire sun, as though the star were not there. These particles are called neutrinos, and they are almost nothing. Right now, as you read this, roughly 100 trillion neutrinos from the sun are passing through your body every second, streaming through your bones and your blood without touching a single atom, and then onward through the solid earth as if it were a window. They are the only messengers that come to us directly from the core. Catch one, and you are reading a note written in the heart of the sun 8 minutes ago. In the late 1960s, a chemist named Raymond Davis set out to catch them. He built a colossal tank holding hundreds of tons of cleaning fluid and buried it nearly 1.5 miles underground, deep inside a gold mine in South Dakota, so that the solid rock above would shield it from every other kind of particle and let only the ghostly neutrinos through. For years he waited, counting the vanishingly rare moments when a single neutrino struck a single atom in his tank and changed it. And he found them. He proved, for the first time in history, that the fusion at the core of the sun was real by catching the ghosts it emits. It was one of the most astonishing experiments ever performed. But there was a twist, and the twist itself became a 30-year mystery. Davis counted the neutrinos, and there were too few. He found only about a third of the number the theory predicted. 2 out of every 3 solar neutrinos seemed to vanish on the way from the core to his tank. For decades, this was called the solar neutrino problem, and it gnawed at physicists, because it suggested either that our model of the sun was wrong, or that something about the neutrinos themselves was not understood. The answer, when it finally came, rewrote part of particle physics. The neutrinos were not vanishing, they were changing. Neutrinos come in 3 types, and they shift from one type to another in flight. And Davis's tank could only detect one of the 3. Once scientists learned to count all 3, the numbers matched the prediction exactly. The sun's furnace was confirmed, the theory vindicated, and a deep secret of the particle world had been pried open, all at once. We can now, in a real and literal sense, see into the heart of our star, and so, piece by piece, a complete picture of the sun's life had been assembled. But a life implies an ending, and the most chilling confirmation that the sun would die came not from theory at all. It came from looking up and finding the corpses of stars that had already died, and realizing that one of them was a preview of our own future. The first hint was old, far older than the discovery of fusion. In 1844, the astronomer Friedrich Bessel was tracking the motion of Sirius, the brightest star in the night sky, and he noticed something impossible. Sirius was not moving in a straight line. It was wobbling, weaving a slow, regular path across the years, as though it were being tugged by an unseen partner orbiting around it. Bessel concluded there had to be a companion star there, a dark one, heavy enough to pull on Sirius but too faint to see. For nearly 2 decades that dark companion remained a ghost, inferred but never glimpsed. Then, in 1862, a telescope maker testing a new lens finally spotted it, a tiny, faint speck of light right where the wobble demanded it be. Sirius had a hidden twin. But when astronomers measured that twin, the numbers made no sense at all. The companion, now called Sirius B, was about as heavy as the sun, yet it was small, astonishingly small, eventually shown to be roughly the size of the Earth. Pack the entire mass of the sun into a ball, the size of our little planet, and you get a density so extreme it sounds like a misprint. A single spoonful of the material inside Sirius B would weigh as much as a small truck. Arthur Eddington, the same man who first proposed fusion, captured the disbelief of the entire field in a single famous passage. He imagined the star sending us a message, and the message read, in his words, that it was made of material thousands of times denser than anything we had ever encountered, that a ton of it could be carried in a matchbox. And the reply most scientists wanted to give, Eddington admitted, was simply to tell the star to be quiet and stop talking nonsense. But it was not nonsense. Sirius B was the first known example of a white dwarf, and a white dwarf, scientists slowly came to realize, is what a star like the sun becomes when it dies. It is the burnt-out, collapsed core left behind after the fire goes out, a stellar ember so dense that the ordinary structure of matter has been crushed away. When you look at Sirius B tonight, you are not looking at a curiosity. You are looking at the future. You are seeing in advance the cold, dense remnant that our own sun is destined to become. And once astronomers understood this, the Hertzsprung-Russell diagram transformed from a simple map into something far more haunting. That great diagonal band, the main sequence, was not the whole story. Off the band, in the upper right corner, sat a scattered population of cool but enormously bright stars, the red giants, swollen and luminous. And down in the lower left corner, faint and hot, sat the white dwarfs, the embers. These were not different kinds of stars living separate lives. They were the same stars at different ages. A star is born onto the main sequence, lives its long stable prime there, and then, when its core fuel runs low, it leaves the band, swelling first into the red giant region, and finally collapsing down into the white dwarf graveyard. The diagram was not a snapshot. It was a story, told all at once, the way a single photograph of a crowded street might catch infants and elders and everyone in between, letting you read an entire human lifespan from one frozen instant. The sky is full of stars at every stage of dying, and the sun's whole future is written across it, if you know how to read. So the picture is complete, and it is merciless in its clarity. The sun is a vast, slow, self-regulating furnace, fusing hydrogen into helium on a quantum loophole, balanced for billions of years between fire and gravity, brightening steadily as it ages. And when its core fuel is spent, it will follow the same path we have watched other stars follow countless times across the galaxy. It will leave the main sequence, it will swell into a red giant, and it will end as a white dwarf, an Earth-sized ember of impossible density, drifting cold and dark where a star once blazed. We know this not because we hope it or fear it, but because we have seen it happen, again and again, written in the light of dying stars. Let me put the scale of this furnace into something you can hold in your mind. The sun is so large that if it were hollow, you could pour roughly 1,300,000 Earths inside it and still have room to spare. Its core, where the fusion happens, is squeezed to a temperature of about 15 million degrees Celsius, and to a density many times that of solid lead, yet it behaves as a gas because of the unimaginable heat. If you could somehow shrink the entire sun down to the size of a basketball and set it on the ground in front of you, then on that same scale, the Earth would be a grain of sand about the width of your fingernail, sitting roughly 26 meters away, lost in the dark. And here is a comparison that captures just how slow and patient this furnace truly is. You might imagine that the center of the sun, gram for gram, blazes with more raw power than anything you know. It does not. Gram for gram, the core of the sun produces less heat than the inside of a compost heap or a living human body. The sun is overwhelming, not because each piece of it is so fierce, but because it is so vast. There is simply so much of it, all glowing faintly at once, that the total becomes a force that lights an entire solar system. The sun is a mountain of embers, not a single blinding flame. Now hold one more number. The light that warms your face left the surface of the sun about 8 minutes ago, crossing roughly 150 million kilometers of empty space to reach you. But the energy carried in that light is far, far older than 8 minutes. A single packet of light energy created in the core has to fight its way out through the crushing layers above it, bouncing and scattering, absorbed and re-emitted countless times, taking, by many estimates, tens of thousands of years to claw its way from the center to the surface. The sunlight on your skin tonight may have begun its journey when our species was first learning to paint on the walls of caves. Let that settle for a moment. The warmth you feel is ancient. With fusion understood, astronomers could finally do something that had been impossible before. They could read a star's age and predict its future, the way a doctor reads a life from a single drop of blood. The key was a chart drawn up in the early years of the 20th century by Ejnar Hertzsprung and, independently, by that same Henry Norris Russell. On this chart, every star is plotted by its brightness and its colour, and when you plot them, a stunning pattern appears. Most stars do not scatter randomly across the chart. They fall along a single sweeping line, a great diagonal band, running from hot, brilliant blue stars at one end to cool, dim red stars at the other. This band is called the main sequence, and the sun sits right in the middle of it. That line is not just a pattern, it is a stage of life. A star spends the long, stable prime of its existence on the main sequence, quietly fusing hydrogen in its core, in a steady balance between the outward push of fusion and the inward crush of gravity. The sun has been on that line for around 4.5 billion years, and it has, according to current models, roughly 5 billion more to go before its core hydrogen finally runs dry. The sun is middle-aged. We have caught it almost exactly at the halfway point of its life. There is a clue to the sun's restlessness hidden in the deep history of the Earth itself, and it is a puzzle scientists call the faint young sun paradox. When the sun first ignited, billions of years ago, the same models that predict its future tell us it was considerably dimmer than it is today. By some estimates, only about 70% as bright. A sun that much fainter should have left the early Earth frozen solid, locked under global ice, with no liquid water anywhere on its surface. And yet the geological record is clear. The young Earth had liquid oceans. It had rivers. It almost certainly had life. The math says the early Earth should have been a frozen ball, and the rocks say it was warm and wet. Something does not add up, and scientists still argue over the full explanation, reaching for thicker blankets of greenhouse gases in the ancient atmosphere to make up the difference. But buried inside this paradox is a fact that should make you sit up. The only reason the paradox exists at all is that the sun really has been growing brighter, steadily, this entire time. The faint young sun is not a guess. It is a consequence of the same fusion physics that powers the star, and the brightening it implies is still happening right now, and will keep happening until it becomes lethal. This is where the idea of the habitable zone enters the story, and it is more fragile than its comforting name suggests. Around every star there is a band of space, a thin ring at just the right distance, where a planet can hold liquid water on its surface. Too close to the star and the water boils away. Too far and it freezes. The Earth sits comfortably inside the sun's habitable zone today. But that zone is not fixed in place. As the sun brightens, the entire habitable band creeps slowly outward, away from the star, like a circle of warmth retreating across a cooling floor, and Earth, anchored in its orbit, cannot follow it. The planet that sits safely in the warm zone today will, as the centuries pile into eons, find that zone sliding past it and away, leaving Earth behind on the scorching inner edge. The sun does not have to swell or explode to doom this world. It only has to keep doing exactly what it is doing now. It only has to keep getting brighter. But this is where the comfort ends and the unease begins, because that long stable prey is not perfectly stable at all. The sun has a secret that the smooth golden disk in the sky hides completely. It is getting brighter, slowly, relentlessly. It is turning up its own heat. As the core fuses hydrogen into helium, the helium ash accumulates and the core grows denser, which forces the central reactions to run a little hotter and a little faster with every passing age. The result is a star that is not a steady lamp but a rising one. The sun today is already noticeably brighter than it was when the Earth first formed, and with every billion years that passes, its output climbs by roughly 10%. That single fact rewrites the entire timeline of life on this world, because long, long before the sun ever reaches the dramatic violence of its old age, long before it swells or reddens or collapses, that creeping brightness will quietly cross a line, and on the day it does, the planet you live on will begin to die. The foundation has been laid. We know what the sun is, what feeds it, and how long it can last. But that foundation hides a flaw that turns the story far darker than a simple count of years. The sun is not waiting patiently to die in 5 billion years. It is already turning against us right now by degrees, and the first casualty will not be the sun at all. It will be Earth. For most of human history, when people imagined the end of the sun, they imagined it going out. A flame burning lower and lower, until one day it gutters and dies, and the sky goes dark and cold. It is a peaceful image. It is also completely wrong. The death of the sun is not a fading. It is an escalation. The sun will not die by growing weaker. It will die by growing stronger and brighter and larger, until it becomes something its own planets cannot survive. The villain in this story is not darkness. The villain is light. Too much of it, for far too long. And the most unsettling thing about this villain is that it has already arrived. It is here, right now, working against us in slow motion. The sun you saw today is brighter than the sun your distant ancestors saw, and it will be brighter still for whoever looks up 100 million years from now. This is not a threat waiting in the far future. It is a process already underway, and the first thing it will destroy is not the sun, and not some distant world. It is the thin film of life clinging to the surface of the Earth. Let me walk you through what is actually going to happen in order, because each stage is more extreme than the one before it, and the first stage is far closer than almost anyone realizes. Most people, asked when the sun will become dangerous, will answer 5 billion years. That is the number you hear. That is the number for when the sun runs out of core hydrogen. But that number is a lie of omission, because it describes the death of the sun, not the death of life on Earth. And those two events are separated by an almost unimaginable gulf of time. The biosphere does not have 5 billion years. By the best current estimates, it has something closer to 1 billion, possibly less. Here is why. As the sun's relentless brightening continues, it will gradually force the Earth's temperature upward, no matter what we do. Within roughly 1 billion years, the sun is expected to be bright enough to push the Earth past a fatal threshold. The oceans will begin to evaporate in earnest, and water vapor is itself a powerful heat-trapping gas. so the warming feeds on itself. More heat lifts more water into the air, and more water in the air traps more heat, in a runaway loop that does not stop. The seas do not gently recede. They boil into the sky. The earth wraps itself in a thick, scalding shroud of steam, and then, slowly, the sun's radiation strips the hydrogen out of that water vapor at the top of the atmosphere and blows it away into space, one molecule at a time, until the water is simply gone. Forever. The planet that holds the only known oceans in the universe will be wrung dry like a cloth, and it will never have oceans again. And it may begin even sooner than that, through a quieter door. Plants are the foundation of nearly all life on land, and plants depend on carbon dioxide. But the same rising heat accelerates the slow chemical weathering of rock, which pulls carbon dioxide out of the air over geological time. Some models suggest that within as little as 600 million years, the level of carbon dioxide could fall so low that most plants can no longer perform photosynthesis. If that happens, the green collapse comes first. The forests starve, the food chains built upon them unravel, and the great drying of the oceans simply finishes a planet that has already lost its living heart. Let that sink in for a moment, because the scale of it is hard to hold. Life has clung to this planet for an immense span of time already, through ice ages and asteroid strikes and continental upheavals, and yet the remaining window for that life, before the sun's brightening renders the surface uninhabitable, may be shorter than the time life has already existed here. We are not at the dawn of life on Earth. By the cruel clock of the sun, we may be closer to the afternoon. If you compress the entire habitable lifespan of the Earth's surface into a single day, our species would have arrived only in the final fraction of a second before dusk. And dusk, in this picture, is the sun growing too bright for anything to live beneath it. There is something almost unbearable in imagining the long, slow retreat of life across those final hundreds of millions of years. It will not vanish all at once. Life is stubborn, and it will fight for every degree. As the surface heats and the air thickens with moisture and then loses its carbon dioxide, the large and complex creatures will go first, because they need the most, and they are the most fragile. The great forests will thin and fail. The animals that depend on them will follow. Step by step, the living world will simplify, falling back toward the hardy, the small, and the simple, until the last complex life retreats into whatever cool, shaded refuges remain. The deep oceans before they boil, the polar regions before they bake, caves and crevices where the heat takes longest to reach, and then, in the end, even those refuges will fail, and the last chapter of life on Earth will belong to the same kind of creatures that wrote its first chapter. The most resilient organisms on our planet are not the large and clever ones. They are the microscopic ones, the bacteria, and the simple single-celled life that can endure heat and dryness and salt and radiation that would kill anything more complex in an instant. There are microbes alive today that thrive in near-boiling hot springs, that survive baked into desert rock, that live miles beneath the surface in the dark warmth of the crust, sipping energy from chemistry alone and never needing the sun at all. These will be the last to go. As the surface becomes an oven and the oceans shrink to scalding, shrinking pools, life will retreat downward and inward, into the deep rock and the last hidden reservoirs of water, holding on in pockets of tolerable warmth long after the open world above has become uninhabitable. For a time, perhaps a long time, the Earth will still be, technically, a living world, even as its surface bakes to lifeless stone, but the brightening will not stop. The deep water will eventually cook away. The temperatures even underground will climb past what any chemistry of life can bear, and somewhere, in some final warm pocket of rock, the last living cell on Earth will quietly cease to function, ending a story that will have run by then for billions of uninterrupted years. There will be no witness. There will be no record. The most extraordinary thing we know of in the entire universe, the presence of life on a world, will simply switch off, in the dark, beneath a sun grown too bright to allow it, and the Earth will become exactly the kind of dead, sterilized rock we see when we look at the scorched inner planets beside us. A second Venus, where once there had been an ocean and a sky full of birds. There is a particular cruelty in the order of events, and it is worth naming plainly. The planet will not be destroyed when this happens. It will still be here, the same size, the same mass, turning on the same axis, orbiting the same star. The continents will still be there, the mountains, the dry basins where oceans used to be. From a great distance, it would still look like a world, but it will be a corpse of a world, a perfectly preserved tomb of a planet that once teemed with life, circling on for billions of years more before the sun ever reaches out to physically destroy it. The death of life and the death of the planet are two entirely separate events, separated by an almost unimaginable gulf of time. Life ends first, in the brightening. The planet itself endures, lifeless, for ages afterward, until the red giant finally comes. We tend to picture the Earth's end as a single dramatic moment of fire. But the truth is slower and lonelier, and in some ways far sadder than that. The fire comes at the very end. The silence comes long, long before. And in the very end, when even those refuges fail, the final inhabitants of the Earth will likely be what the first inhabitants were: microbes. Tough, single-celled organisms, huddled in the last warm but not yet lethal pockets of a dying world, clinging to existence in superheated rock and acidic pools, the way they did in the planet's distant youth. The story of life on Earth may end almost exactly where it began, with microscopic survivors in extreme places, the difference being that the first time the planet was warming into habitability, and the last time it will be roasting out of it. The book of life will close on the same kind of creature that opened it, and there will be no one left to notice the symmetry. Pause on the timescales here, because they break the mind a little. We talk casually about 1 billion years as though it were just a big number. But 1 billion years is so long that the arrangement of the continents themselves will be unrecognizable. Mountain ranges that do not yet exist will rise and erode completely to flat plains in that span. The familiar map of Earth, the shapes of the oceans and the lands, will be scrambled and reformed many times over before the sun's brightening finishes its work. Whole new chapters of geological history, longer than everything that has happened since the first life appeared, will unfold and pass before the final drying. The sun is patient. It has all the time in the universe, and it will use every bit of it, turning up the heat by imperceptible degrees, until the only planet we know of that ever held life becomes as dead and dry as the worlds beside it. The death of life on Earth, as horrifying as it is only the opening act. The sun itself will barely notice. It will keep right on shining, keep right on brightening, for billions of years after the last ocean has boiled away and the last living thing has perished. The drying of the Earth is a footnote in the sun's biography. The real death of the sun, the violent, transforming, world-ending death, does not begin until the furnace at its center finally runs dry. And to understand that, we have to go back to the war we described earlier, the war between gravity and fire, because everything that follows comes from the moment that war is finally lost. Remember the thermostat. For billions of years, the sun holds a perfect balance. Gravity pulls in, fusion pushes out, and the two stay locked in an exact draw, with the fusion rate quietly regulating itself to keep the star steady. But that balance depends on one thing. It depends on there being hydrogen in the core to fuse, and the core is, slowly, filling up with ash. Every fusion reaction turns hydrogen into helium, and that helium sinks to the very center and accumulates there, inert, unable to fuse at the temperatures the sun can currently reach. Over billions of years, a growing ball of dead helium ash builds up at the heart of the star, a core within the core, producing no energy at all. And here is where the thermostat begins to fail. In roughly 5 billion years from now, the sun will have exhausted the last of the hydrogen in its central core, leaving behind a sphere of helium that it cannot yet ignite. With no fusion in the center to hold it up, that helium core has nothing to resist gravity, and so it begins to contract, squeezing tighter and growing hotter under its own crushing weight. This is the moment the long stability ends. The contracting core heats up so much that it ignites a shell of hydrogen around itself, a layer of fresh fuel just outside the dead center, and this shell burns furiously, far faster and hotter than the old core ever did. Now something deeply strange happens, something that runs against every intuition. You would think that a hotter, fiercer fusion would make the sun shrink and brighten in place. Instead, it does the opposite. The flood of energy from that burning shell pours outward into the sun's vast envelope and pushes it apart. the outer layers of the sun begin to swell, ballooning outward, expanding to enormous size. And as they expand, they spread the same heat over a far larger surface, so the surface itself cools and reddens, shifting from blinding white gold to a deep, sullen red. The sun is no longer a tidy star. It has become a red giant. The thermostat is broken. Gravity has lost its grip on the outer star, and there is nothing to stop the expansion. The numbers here are difficult to even comprehend. As a red giant, the sun will not grow by a little. It will grow by a factor of roughly 250. Picture the sun in the sky today, a disk you could cover with your thumbnail at arm's length. Now imagine it bloating outward until it swallows the space where Mercury orbits, then the space where Venus orbits, swelling at its peak to something on the order of 256 times its current radius, large enough to reach out roughly to the distance of Earth's own orbit. At the same time, it will blaze with a brightness somewhere between 2,000 and 3,000 times greater than today. The gentle golden sun will have become a vast, bloated, blood-red furnace filling half the sky of any world unlucky enough to remain nearby. Mercury has no chance. It will be the first to go, swallowed and vaporized as the swelling sun rolls over its orbit. Venus follows, consumed in the same expansion. 2 entire planets, erased, melted into the outer layers of the dying star as though they had never existed. And then the red giant reaches outward toward the 3rd planet, toward Earth. And here at last we arrive at the oldest and most fiercely debated question in this entire story. When the sun reaches its full and terrible size, will it swallow the Earth too? This is where the investigation gets genuinely contentious, and where you can watch the greatest minds in science change their answer again and again across a full century. The question was first taken seriously back in 1924 by the British physicist James Jeans, who wondered aloud what would become of the Earth when the sun entered its red giant phase. And ever since that moment, scientists have gone back and forth, reaching opposite conclusions in waves, because the truth turns out to balance on a knife's edge between 2 opposing forces, and which one wins decides whether our planet survives or is destroyed. On one side is a strange and hopeful effect. As the sun ages and swells, it does not only grow, it also loses mass. A red giant blows off huge quantities of its own material in a powerful wind, shedding matter into space. And here is the crucial point. A planet's orbit is held by the gravity of its star, and that gravity depends on the star's mass. So, as the sun grows lighter, its grip on the Earth weakens, and the Earth's orbit drifts gradually outward, spiraling away from the danger, like a stone on a string when the string is slowly let out. By this logic, the Earth might be carried to safety, lifted out of the sun's reach by the very mass loss of the dying star. For a time, this gave astronomers genuine hope. They calculated that the Earth's orbit would expand, perhaps by enough to escape, and they concluded the planet would survive as a scorched, lifeless cinder, but survive. But there is a second force, and it works in exactly the opposite direction. As the sun swells into a bloated giant, its outer atmosphere becomes enormous and tenuous, reaching far out into the solar system, and the Earth, ploughing through that thin outer gas, feels a drag, a faint but ceaseless friction that bleeds energy from its orbit and pulls it inward. There is also a subtler effect. The Earth raises a tidal bulge on the giant sun, and that bulge tugs back on the Earth, sapping its orbital energy and dragging it down toward the star. So the contest is set. Mass loss pushes the Earth outward toward safety. Tidal drag and atmospheric friction pull it inward toward destruction. The fate of the entire planet comes down to which of these 2 forces is stronger. And for decades, every time someone refined the calculation, the answer flipped. This is one of those moments where everyone thought they had the answer, and then the next generation proved them wrong. For a while, the orbital expansion camp seemed to win, and the comforting verdict was that Earth escapes. Then, in 2008, a careful and influential study by the astronomers Klaus-Peter Schroeder and Robert Smith ran the full calculation with the inward drag included, and delivered a far grimmer conclusion. The expanding sun, they found, would engulf the Earth just before reaching the very tip of its red giant phase. The orbital expansion, in their numbers, simply was not enough. The drag won. The Earth would be swallowed, with the sun still having a little more growing left to do, plunging our planet into the searing outer layers of the star, where it would meet particles of stellar gas, slow spiral inward and be utterly destroyed. And it gets worse, because the more recent work has tended to harden that grim verdict rather than soften it. In recent years, independent teams using different methods have again calculated Earth's fate, and the latest analyses have leaned toward engulfment. One recent calculation found that the Earth's outward drift from the Sun's mass loss would amount to only a tiny shift far too small to escape the swelling giant. The consensus among most astrophysicists today is that the inward drag overwhelms the outward push, and that the Earth, in the end, is consumed. Mercury, Venus, and very likely Earth, all three inner worlds, melted into the body of the dying Sun. There remains genuine scientific disagreement at the edges. A minority of scenarios still allow the Earth to escape as a burned-out husk, but the weight of evidence now points to the darker outcome. The planet that gave rise to everything you have ever known is most likely destined to be erased without a trace, leaving behind no proof that it, or we, were ever here. 3 scaled comparisons can help you feel the violence of what is coming. First, the surface of the red giant sun will reach almost to where Earth orbits today, which means that if you could somehow stand on a surviving outer world and look back, the sun would not be a small bright disk, but a wall of dull red fire, taking up a huge fraction of the entire sky, close enough that its swollen edge would seem to loom directly overhead. Second, the brightness. A sun 3,000 times more luminous than today would not merely warm the inner solar system, it would cook the outer one. Worlds that are frozen wastelands now, far beyond the reach of present sunlight, would suddenly find themselves bathed in heat. And third, consider the speed of the final act. The sun takes billions of years to crawl through its stable life, but once the red giant expansion truly begins, the swelling to its maximum size happens, by cosmic standards, in a flash, a span of perhaps a few million years, the blink of an eye against the long age that came before. Now, just when you think the story has reached its peak of violence, the dying sun has one more shock waiting, and it is perhaps the strangest event in the entire sequence. But before the helium flash, consider what the red giant does to the rest of the solar system, because the destruction of the inner planets is only part of the upheaval. The same expansion and brightening that dooms the Earth will utterly transform the worlds beyond it, and in a cruel twist, it will briefly bring warmth and possibility to places that are frozen tombs today. Out where Jupiter rules, its giant moons are presently locked in ice, their oceans, where they exist, buried under frozen crusts kilometers thick. But when the sun swells to 3,000 times its current brightness, the heat will reach out and touch those distant moons. The ice on a world like Europa could melt. For a window of time that might last tens or even hundreds of millions of years, some of these outer moons could become temperate, water-rich places, a strange, fleeting habitable zone blossoming in the cold outer dark just as the inner solar system burns. Saturn's largest moon, Titan, with its thick atmosphere, might warm into something resembling an early Earth with liquid pooling on its surface. The death of the inner worlds may be the brief dawn of the outer ones. The gas giants themselves will not be swallowed. They orbit far beyond the reach of even the bloated red giant sun, but they will not be untouched. As the sun sheds enormous quantities of mass in its dying winds, its gravitational grip on the whole system loosens, and the orbits of Jupiter, Saturn, Uranus, and Neptune will all drift outward, widening as the star that anchors them grows lighter. The entire architecture of the solar system, the careful spacing of the planets that has held for billions of years, will be rearranged, and the moon, our own pale companion, faces its own quiet doom in the inner cataclysm. As the Earth is dragged toward the swelling sun, the moon will be caught in the same destruction, the two worlds that have circled each other for billions of years, finally parting only to be consumed together. And here is a detail that captures the sheer scale of the mass the dying sun throws away. In the late stages, as the sun convulses through what astronomers call the asymptotic giant branch, its second, even larger giant phase, it can lose mass at a rate so enormous that it sheds the equivalent of a substantial fraction of an entire Earth's worth of material every single year, flinging it off into space on a powerful wind. The sun is not only dying, it is disassembling itself, casting its own body outward into the dark in great expanding shells of gas. By the time it is finished, the Sun will have thrown away nearly half of all the mass it was born with. This second giant phase, the asymptotic giant branch, is where the dying star becomes truly unstable, and it is worth lingering on because it is the immediate prelude to the end. Here the Sun is burning helium and hydrogen in two separate shells wrapped around its dead carbon-oxygen core, and these shells do not burn steadily. They burn in fits. Every so often, the helium shell ignites in a sudden surge called a thermal pulse, a brief flaring that ripples through the whole star and heaves another portion of its outer layers off into space. Between pulses the star quiets, then flares again, a slow and violent heartbeat with thousands of years between each beat. With every pulse, the Sun loses more of itself, and the great convective currents in its body can dredge up freshly made carbon from deep inside and carry it to the surface, so that the dying star's outer layers grow rich in soot and carbon, the raw material of organic chemistry, scattered outward into the galaxy. Stop here for a moment and consider what that means, because it is one of the quiet hinges of this entire story. The carbon being forged in the heart of the dying Sun and flung out into space. That is not waste, that is seed. The heavy elements built inside stars and released in their deaths are the very atoms that go on to form new worlds, new chemistry, and, on at least one world, new life. The dying Sun, in scattering its body across the galaxy, is doing exactly what some earlier dying star did to make the Sun and the Earth and you. We will return to this idea later, because it is the most profound reversal in the whole tale. The moment when the death of a star turns out to be the source of everything. For now, hold this thought. The Sun's destruction is not only an ending, it is also a kind of sowing. The numbers behind all of this are striking, but the experience would be stranger still. Picture the sky of a surviving outer world during the asymptotic giant branch. The Sun is no longer a star in any familiar sense. It is a vast, pulsing, sullen red presence, surrounded by glowing shells of gas it has cast off, brightening and dimming in slow convulsions, wrapped in clouds of its own carbon soot. It is a star coming apart at the seams, and it does so not quietly, but in great heaving breaths, each one scattering more of itself into the void. This goes on for a relatively brief span by stellar standards. The asymptotic giant branch lasts perhaps 1,000,000 years or so, an instant against the 10 billion years of stable life that preceded it. The Sun spends almost its entire existence as a quiet, steady star and then unravels in a geological heartbeat at the end. It is called the helium flash, and to understand why it is so terrifying, you have to understand what has been happening at the very center of the star. While the swollen red giant burns hydrogen in a shell, the dead helium core at its heart keeps contracting and heating under gravity, getting denser and denser, hotter and hotter. But this core is no longer ordinary matter. It has been crushed into a bizarre state called degenerate matter, where the electrons are packed so tightly that they resist further compression through a deep rule of quantum physics, not through heat, and this creates a hidden danger. Normally, the Sun's thermostat works because heat makes gas expand and cool, but degenerate matter does not behave that way. You can pour heat into it and it will not expand. It just gets hotter and hotter while staying the same size, with no safety valve, no thermostat, nothing to release the pressure. So the core heats up toward the ignition point of helium, which requires the staggering temperature of around 100 million degrees. And when it finally crosses that line, helium fusion ignites. But because the core cannot expand to cool itself, the ignition does not gently stabilize. It runs away. The newly released heat makes the fusion faster, which releases more heat, which makes it faster still, in a violent, explosive, self-amplifying cascade that tears through the core in a matter of seconds to minutes. For that brief, terrible instant, the helium at the center of the dying Sun fuses with a fury that is almost impossible to describe. The power output of the core during the helium flash can briefly rival the combined light of an entire galaxy of hundreds of billions of stars. A flash of raw energy, deep inside the Sun, equal to all the stars of the Milky Way blazing at once. And here is the part that makes the helium flash so eerie. From the outside, you would see almost nothing. All of that galaxy-scale energy is absorbed by the vast overlying layers of the star, swallowed and muffled before it can reach the surface. The Sun does not visibly explode. It does not flare across the sky. The most violent single event in the sun's entire existence happens in total secrecy, buried under hundreds of thousands of kilometers of star, its unimaginable power spent entirely on rearranging the sun's own interior. The flash quietly lifts the degeneracy of the core, the thermostat is restored, and the sun settles into a new, briefer phase of stable helium burning. Fusing helium into carbon and oxygen in its center, the very elements that life is built from. But the reprieve is short. Helium is a far poorer fuel than hydrogen, and the sun will burn through it in a fraction of the time, perhaps a little over 100 million years, compared to the 10 billion years its hydrogen lasted. When that helium runs out too, the crisis returns, worse than before. Now the sun has a dead core of carbon and oxygen, and it cannot reach the far higher temperatures needed to fuse those into anything heavier. The sun is too small, too light, to climb that last step. So it repeats the earlier pattern, but more violently, burning helium and hydrogen in unstable shells around the dead core, swelling outward a second time, even larger and more luminous than before, into a final, even more enormous giant phase. And now it begins to throb. The shell burning becomes unsteady, pulsing in great thermal heartbeats, and with each pulse, the sun heaves more of its outer material off into space. The dying star starts to come apart, shedding its envelope layer by layer, exhaling itself into the dark. This is the moment everything has been building toward, and it is here, at the threshold of the sun's final transformation, that the full strangeness of the story comes into focus. But here's what makes this truly terrifying. We are not guessing at any of this. We are not extrapolating from equations alone, hoping the math holds. We have watched it happen. Out there in the galaxy, scientists have caught dying stars in the very act of swallowing their planets, have photographed the glowing shrouds of stars in the process of casting off their bodies, and have stared directly at the cold, dense corpses of stars that finished dying long ago. The death of the sun is not a theory we have to take on faith. It is a documented event, playing out across the sky in countless places, captured by our telescopes, and in at least one case, a team of astronomers watched a star like our own consume a world like ours, and understood, with a chill, that they were looking at a home movie of the end of the Earth. For more than 2 centuries, the death of the sun was something scientists could only reason their way toward, never witness. The timescales are so vast that no human will ever see the sun complete even a single step of its dying. We will not watch it swell, we will not see it shed its skin. Every human who has ever lived, and every human who ever will, has caught the sun at essentially the same frozen instant of its long life, like a single still frame pulled from a film that runs for 10 billion years. So how could anyone possibly know what comes next? The answer is the most ingenious thing about this entire field. We cannot watch our sun die, but the galaxy is full of other suns, billions of them, all at different stages of the same journey. And by collecting the dying ones, by photographing stars caught at every point along the path, scientists assembled the whole movie out of 1 billion separate frames. This is the story of how they did it, and of the moment they finally caught a star in the act of killing a world. It begins, like so much in astronomy, with a misunderstanding. In the 1780s, the astronomer William Herschel, sweeping the sky with his enormous homemade telescopes, kept finding small, round, glowing patches of light. Through his lens they looked like soft, fuzzy disks, pale and circular, vaguely greenish, not unlike the faint disk of a distant planet such as Uranus, which Herschel himself had discovered. So, he gave them a name that has stuck for more than 2 centuries, even though it turned out to be completely wrong. He called them planetary nebulae. They have nothing to do with planets. But the name endured, a fossil of an old mistake, attached forever to some of the most beautiful and revealing objects in the sky. For a long time, nobody knew what these glowing rings and shells actually were. They came in astonishing shapes, perfect rings, hourglasses, butterflies, great staring eyes of gas. The Ring Nebula in the constellation Lyra hangs in the sky like a smoke ring blown by something enormous, sitting roughly 2,500 light-years away. The Helix Nebula, one of the closest, only about 650 light-years from us, glares out of the dark like a vast eye, a luminous iris of gas surrounding a tiny, brilliant point at its center. The cat's eye, the dumbbell, the butterfly, each one a sculpture of glowing gas, intricate and strange. And at the heart of every single one of them, if you looked closely, there was always a tiny, fiercely hot point of light. A small white star, burning at the center of all that expanding gas. The hope, as astronomers studied these objects, was that they might explain a piece of the puzzle nobody else could. And slowly the truth came together, and it was breathtaking. These were not clouds where stars are born. They were the opposite. They were stars in the act of dying. That glowing shell of gas was the cast-off body of a star like the Sun. The very outer layers we described being heaved off in the asymptotic giant branch, now drifting outward into space, lit up and made to glow by the searing radiation of the exposed core left behind. And that tiny blazing point at the center was the corpse itself, the newborn white dwarf. We were looking, in these gorgeous luminous rings, at exactly what the Sun will become. A planetary nebula is the death of a sun-like star frozen in a photograph, and there are thousands of them scattered across the sky. The battle to understand them in detail took the most powerful instruments ever built. When the James Webb Space Telescope opened its eye on the universe in the early 2020s, it turned that eye on these dying stars, and what it revealed was almost overwhelming in its detail. Webb photographed the Ring Nebula and the Southern Ring Nebula in stunning depth, peeling back the layers of expelled gas and showing structures no one had ever seen. Concentric arcs and shells, evidence of the dying star pulsing and shedding in waves, exactly as the thermal pulse model predicted. In the Southern Ring, Webb even revealed that the dying star at the center had a hidden companion stirring its ejected gas into complex spirals. The math and the models had said the Sun would cast off its body in expanding shells, and here, in breathtaking infrared clarity, were other suns doing precisely that. There is something poignant hidden in the planetary nebulae, and it has to do with time. These glowing shells are not permanent. They are among the most fleeting objects in the entire sky. A planetary nebula lasts only about 10,000 to 20,000 years before the expanding gas drifts apart and fades into the surrounding darkness, the cast-off material dispersing until it can no longer be seen. Against the 10 billion years of a star's life, that is the briefest of flickers, a candle flame that flares and dies in an instant of cosmic time. Every sun-like star in the galaxy is expected to produce one of these luminous shrouds when it dies. And yet, because each one glows so briefly, only a few thousand are visible across the whole of our galaxy at any given moment. We are not seeing all the deaths. We are seeing only the ones that happen to be dying right now, caught in their tiny window of visibility. The sky is a vast graveyard, but we can only see the freshest graves, the ones still glowing. The variety of their shapes turned out to be a puzzle in itself. If a dying star simply puffed off its outer layers evenly in all directions, every planetary nebula should be a simple round shell. But they are not. They come in butterflies and hourglasses, in nested rings and twisted spirals, in jets and lobes and delicate filaments. The butterfly nebula spreads great glowing wings of gas across light years, heated to staggering temperatures by the searing remnant at its heart. The cat's eye is a labyrinth of concentric shells and knots, a structure so intricate it stunned the astronomers who first imaged it in detail. For a long time, no one understood how dying stars could sculpt such elaborate forms. The leading explanations now point to hidden companions, a second star, or even large planets, orbiting the dying star and stirring its expelled gas into these complex patterns, along with powerful magnetic fields and fast jets shaping the outflow. The death of a star, it turns out, is not a simple exhalation. It is a sculpture, shaped by everything around it, and their colors carry their own meaning, written in the physics of glowing gas. The reds that suffuse so many of these nebulae come from hydrogen, energized by the fierce ultraviolet light of the exposed stellar core and emitting light at a specific shade. The eerie greens come from oxygen atoms, stripped of electrons, glowing in a way that puzzled astronomers for years, until they understood the strange low-density conditions that produce it. These are not arbitrary hues. They are the fingerprints of specific elements being lit up by the dying star's radiation, a chemistry made visible, painted across the void. When you look at an image of a planetary nebula, you are seeing the actual composition of a dead star's discarded body, color-coded by nature itself. A sobering question hangs over all of this, and it concerns our own sun specifically. Will the sun even produce a planetary nebula worth seeing? To light up the expelled gas into a glowing shell, the exposed core must be hot enough and the ejection vigorous enough. And some studies have suggested that the sun sits right at the lower edge of the mass needed to produce a bright, visible planetary nebula at all. More recent modelling has concluded that the sun probably will manage to create a faint one, a final, modest monument of glowing gas. But it may be a dim and short-lived thing compared to the spectacular nebulae we photograph around more massive stars. The sun's last gesture, its final scattering of itself into the dark, may be quiet and faint, a pale ring barely glowing for a few thousand years before it too fades and is gone, leaving only the cooling ember at its centre. Even in death, the sun is destined to be unremarkable, just one more ordinary star ending in just the way ordinary stars do. But there was a limit to what a planetary nebula could tell us. A planetary nebula is the aftermath. It is the scene after the death, the body already cooling, the gas already drifting away. It shows you what the sun will leave behind. It does not show you the act itself, the moment a dying star reaches out and destroys a world. For that you would have to get impossibly lucky. You would have to be watching the right star, in the right galaxy, at the exact right moment, out of hundreds of billions of stars, to catch the brief flash of a planet being consumed. For all of history, that seemed like something we would never see. And then, in 2023, we saw it. The discovery began, as these things often do, with a survey that was looking for something else. At Palomar Observatory in California, a project called the Zwicky Transient Facility scans the entire visible sky over and over, night after night, hunting for anything that suddenly changes, anything that flares, brightens, or appears where nothing was before. It is a machine built to catch the universe in the act. And one night, in its torrent of data, it flagged a star that had abruptly brightened by about 100 times, in the constellation Aquila, roughly 12,000 light-years away. A young astrophysicist named Kishalai De and his colleagues began to investigate. And at first the event was a puzzle. It was not bright enough to be two stars merging. It did not match the signature of an ordinary stellar outburst. Something stranger was going on. The crucial clue came from infrared light. Using data from a NASA infrared survey called NEOWISE, the team found that the star had actually begun brightening in the infrared about a year before the visible flash, which meant the event was wrapped in dust, cool material being thrown off and condensing around the star. When they pieced together the full picture, the conclusion was staggering, and it was unlike anything ever directly observed. They had caught a star swallowing a planet. A world roughly the size of Jupiter, orbiting close to its aging star, had spiraled inward until it plunged into the star itself, releasing a burst of light and a shroud of dust as it was destroyed. For the first time in the history of science, human beings had directly witnessed the death of a planet at the hands of its own star, and the team understood immediately what they were really looking at. This was not just some distant catastrophe. It was a preview of home. The star, an aging sun-like star around 10 billion years old, was doing exactly what our sun will one day do to its own inner worlds. Kishalade put it in words that land like a stone dropped into still water. He said simply that they were seeing the future of the Earth. He went further, painting a picture that should make anyone shiver. If some distant alien civilization happened to be watching our solar system from thousands of light years away at the moment the sun engulfs the Earth, they would see almost exactly this: a sudden flash of brightening, a puff of dust, the unremarkable signature of a small world being swallowed whole, indistinguishable from 1,000 other such flashes across the galaxy. The end of everything we have ever been, reduced to a faint flicker in someone else's telescope. The numbers are striking. From that single observation, astronomers calculated that these planet-swallowing events should happen surprisingly often, perhaps a few times every year, somewhere in our galaxy alone. Planetary engulfment, it turns out, is not a rare freak event. It is a routine part of how stars die, a common fate for worlds that orbit too close to stars entering old age. The galaxy is quietly devouring planets all the time, and we had simply never managed to catch it in the act until now. The death of the Earth, in other words, is not special. It is ordinary. It is what stars do. But this story had one more twist waiting, and it is a perfect example of how science corrects itself when better evidence arrives. Because 2 years later, in 2025, astronomers pointed the James Webb Space Telescope at that same dying star to study the aftermath in detail. And Webb told a different story than everyone had expected. The original interpretation had been that the star, aging into a red giant, had swelled outward and engulfed its planet as it expanded. But Webb's sensitive infrared instruments revealed that the star did not appear to have puffed up into a giant at all. Instead, the evidence pointed to the planet's own orbit decaying, the world spiraling inward on its own over time, drawn closer and closer until it plunged into a star that had not yet swollen to meet it. Webb found a hot disk of gas swirling around the star, and an expanding cloud of cooler dust enveloping the scene, the wreckage of the consumed world. The data had contradicted the first hypothesis, and rather than hide it, the scientists revised the picture. The planet had not been reached by an expanding star. It had fallen. That distinction matters, and it teaches something important about our own fate. There are at least 2 ways for a star to claim a planet: by swelling outward to engulf it, or by the planet's orbit slowly decaying until it falls inward. The Sun will most likely take the first path, swelling into a giant that reaches out to grab the Earth. But the lesson of that distant dying star is that the galaxy has more than one way to end a world, and that we are still learning the details by watching it happen elsewhere. We caught one execution in progress, and even then, the precise mechanism surprised us. Honesty compels the admission that there is still much we do not fully understand about exactly how these deaths unfold, which is why scientists continue to hunt for more of them, more flashes, more swallowed worlds, each one a clue to our own ending. So we had read the aftermath in the planetary nebulae, and we had glimpsed the act itself in a distant star eating its world. But there remained a deeper question, the most personal one of all. How do we know the timeline for our own sun? How can scientists claim, with confidence, that our star has roughly 5 billion years left, that the brightening will doom the Earth in about 1 billion, that the helium flash will come at a particular moment? To answer that, they had to do something that sounds impossible. They had to look inside the sun. You cannot see into the sun with light. The core is buried under hundreds of thousands of kilometers of blinding plasma, and no telescope can pierce it. But in the 1960s, astronomers discovered something extraordinary. The sun rings, it vibrates. Its entire surface is heaving up and down in a vast, complex pattern of oscillations as sound waves generated deep inside the sun bounce around its interior and make the whole star quiver like a struck bell. The surface rises and falls in rhythms lasting about 5 minutes, and tens of millions of these notes are sounding all at once, layered together into a cosmic chord no ear could ever hear. And here is the beautiful part. The way those waves travel through the sun depends on what they pass through, on the temperature, the density, the composition at every depth. By carefully measuring the trembling of the surface, scientists could reconstruct the hidden interior, the way a geologist reads the inside of the Earth from the echoes of earthquakes. This science is called heliosismology, and it turned the sun from an opaque mystery into something almost transparent. Networks of telescopes spread around the Earth, and dedicated spacecraft, most famously the Solar and Heliospheric Observatory, launched in 1995 and stationed between the Earth and the Sun, listened to the Sun's vibrations without pause year after year, and what they found confirmed the model with stunning precision. The temperature of the core, the depth of the various layers, the slow churning of the convective zone, the very speed of sound at every level inside the star, all of it matched the predictions of the standard solar model, the same model that forecasts the sun's death. When the heliosismology data came in and lined up with the theory, it was a profound confirmation. We were not guessing about the inside of the sun. We had measured it by listening to it ring, and the measurements agreed with the equations that spell out its doom. Combine that with the neutrinos streaming from the core, and the case becomes airtight. two completely independent windows into the heart of the sun, the ghostly neutrinos born in the fusion reactions and the sound waves echoing through the interior. And both of them confirm the same picture of a star burning hydrogen into helium at a known rate, with a known amount of fuel, on a known schedule toward death. This is why scientists can speak about the sun's future with such confidence. It is not speculation. It is the convergence of theory, of neutrino detectors buried in mines, of spacecraft listening to a ringing star, and of countless dying suns photographed across the galaxy, all telling the same story. The sun will die. It will die in stages, and we know roughly when, which raises the question that no one watching this can avoid asking. But before we ask whether we can escape the sun's death, we have to confront what the sun actually becomes when the dying is done. The cold, dense corpse it leaves behind. Because that final object is one of the strangest things in the universe, and the story of how we came to understand it is a drama of its own, complete with a young genius and the great man who tried to destroy his idea. We met Sirius B earlier, the first known white dwarf, the impossible star that packs the mass of the sun into the volume of the Earth. But understanding why such an object could exist at all and what limits govern it fell to a 19-year-old student from India named Subramanian Chandrasekhar. In 1930, on the long sea voyage from India to England to begin his studies, Chandrasekhar passed the time by working through the physics of dying stars, and he calculated something that would eventually transform astronomy. He realized that a white dwarf is held up not by heat, and not by ordinary pressure, but by a deep quantum rule. The electrons inside it are packed so tightly that they physically resist being crowded any closer, a phenomenon called electron degeneracy pressure, and this resistance is the only thing standing between the corpse and total collapse. But Chandrasekhar saw further. He realized this support has a limit. If the white dwarf is too massive, the electrons are forced to move so fast, approaching the speed of light, that their resistance fails, and nothing can stop the collapse. He calculated that limit precisely. A white dwarf cannot exist above roughly 1.4 times the mass of the sun. Cross that line, and the corpse cannot hold itself up. It must collapse into something even more extreme. This number, now called the Chandrasekhar limit, is one of the most important in all of astrophysics. But when the young Chandrasekhar presented it, the most powerful astronomer in Britain rose to crush it. Arthur Eddington, the same Eddington who had championed fusion, the same one who had marvelled at the density of Sirius B, stood up at a meeting of the Royal Astronomical Society in 1935 and publicly mocked the idea. He declared that there ought to be a law of nature to prevent stars from behaving in such an absurd way, and he dismissed Chandrasekhar's careful mathematics in front of the assembled astronomers of the age. It was a humiliating, unfair attack from the field's most towering figure against a young researcher, and it set Chandrasekhar's reputation back for years. Here again is a moment when one of the greatest minds in science was certain he had the answer, and was simply wrong. Chandrasekhar was right, Eddington was wrong, and nearly half a century later, in 1983, Chandrasekhar received the highest honour in physics for the very work Eddington had ridiculed. The limit stands. It has been confirmed countless times, and it decides the fate of every dying star. For our sun, the verdict of that limit is, in a strange way, merciful. When the sun finishes dying, after it has cast off its outer layers and exposed its core, that remaining core will weigh only about half the mass of the sun, perhaps a little more, well below Chandrasekhar's fatal line. And so the sun's corpse is stable. It does not collapse further. It settles into a white dwarf, an Earth-sized ember of carbon and oxygen, glowing white-hot at first from its leftover heat, and it simply sits there, supported by that quantum resistance of crowded electrons, for an almost endless span of time. This is the sun's true and final form. Not an explosion, not a black hole, a small, dense, slowly cooling diamond of a star, holding the wreckage of everything the sun once was. And here is where the Chandrasekhar limit reveals the gentlest secret of the sun's death. Because there are stars for which the ending is incomparably more violent, and the only thing separating their fate from the sun's is mass. Take a star much heavier than the sun, say 8 or 10 times its mass or more, and the story does not end in a quiet white dwarf. Such a star burns through its fuel in a fraction of the time, fuses heavier and heavier elements in desperate stages, building an iron core that cannot fuse at all, until in a final catastrophic instant, that core collapses past the Chandrasekhar limit in less than a second, and the star detonates as a supernova, one of the most violent events in the universe, briefly outshining an entire galaxy of billions of stars, scattering its guts across light years of space, and leaving behind either an impossibly dense neutron star or a black hole. The bright red star Betelgeuse in the shoulder of the constellation Orion, only about 650 light-years away, is one such doomed giant, and it will one day end exactly this way, blazing so brightly that it may be visible in daylight from Earth. Sit with that contrast for a moment, because it tells us something we ought to find almost comforting about our own star. The Sun is, by the standards of the cosmos, a small and modest thing. We tend to think of it as enormous, and compared to the Earth it is. More than 1,000,000 Earths could fit inside it. But against the great furnace stars of the galaxy, the blue giants and the red supergiants, the Sun is unremarkable, a middling, ordinary star of middling, ordinary mass. And that ordinariness is, in the deepest sense, a mercy. Because mass is destiny for a star, and the Sun's modest mass spares it from the most violent ending nature can devise. The Sun will never explode. It does not have enough mass to fuse the heavy elements that lead to a runaway iron core. It does not have enough mass to collapse past Chandrasekhar's line. When the Sun dies, there will be no supernova, no blinding flash outshining a galaxy, no neutron star or black hole left smouldering in the wreckage. The Sun will die quietly, by stellar standards, swelling, shedding, and settling into a cooling ember, with nothing more violent than the hidden flicker of a helium flash buried deep in its core. Had the Sun been born just 8 or 10 times heavier, the Earth story would have been far shorter and far more dramatic, ending not in a slow brightening over billions of years, but in a sudden cataclysm. We owe our long, calm tenure beneath a stable star to the simple, unremarkable fact that the Sun is not very big. And yet there is a strange debt buried in that violence we are spared. The supernovae of massive stars, terrible as they are also among the most creative events in the universe. The gentlest deaths, the planetary nebulae of stars like the Sun, return carbon and oxygen and nitrogen to the galaxy. But the heaviest elements, the iron, and beyond it, the silver and the gold and the rare metals that we treasure and that life sometimes uses, are forged and scattered chiefly in the deaths of the giant stars, in the supernova blasts and the violent collisions of stellar corpses. So even the explosions we are fortunate to avoid played their part in making us possible. The iron in your blood was very likely born in exactly the kind of cataclysm that the Sun will never suffer. The universe builds its richest ingredients in its most violent furnaces, and then, in gentler deaths like the one awaiting our Sun, it folds those ingredients into new generations of quieter stars and the worlds that circle them. Our calm Sun is in part a child of ancient violence, and it will pass on its inheritance not with a detonation, but with a long, slow, fading sigh. The Sun will never do this. It cannot. It is too small, too light, to climb the ladder of fusion to iron, too far below the line where the catastrophe becomes possible. And so, against every dramatic expectation, the Sun's death is the gentle kind. It will swell and shed and cool, not explode. It will leave a quiet ember, not a black hole. The very ordinariness of our star, the modest mass that has let it burn steadily for so long, is also what spares it the most violent ending. The Sun is too small to die in fire. It will die in fading instead, after its one brief season of swelling. And there is something almost poignant in that the same humble size which made the Sun a stable, life-giving star also condemns it to a slow, undramatic, drawn-out death rather than a blaze of glory. But the corpse the Sun leaves behind is not as inert as it sounds. White dwarfs, it turns out, are not finished with their planets. And this is where one of the most haunting lines of evidence in the entire story emerges. The discovery that we can actually find, and even chemically analyze, the ground-up remains of worlds that their dying stars have destroyed. When astronomers began carefully studying the light of white dwarfs, they ran into a mystery that took a long time to solve. A white dwarf's surface gravity is so ferociously strong that any heavy element should sink out of sight almost immediately, leaving only the lightest elements floating at the top where we can see them. The surface of a white dwarf should be pure, swept clean of anything heavy. And yet, when scientists spread the light of many white dwarfs into a spectrum and read the fingerprints in it, they found heavy elements that simply should not be there. Calcium, magnesium, iron, the chemical signatures of rock and metal staining the atmospheres of these dead stars, even though such elements should have vanished beneath the surface in a geological eye blink. The explanation, once it came together, is one of the most quietly chilling discoveries in modern astronomy. Those heavy elements are there because the white dwarf is, right now, eating the remains of its own planetary system. After a star dies, the surviving asteroids, comets, and broken pieces of its former planets continue to orbit the white dwarf, and from time to time, one of them wanders too close, where the white dwarf's immense gravity tears it apart into a stream of dust and rubble that rains down onto the star's surface. So the heavy elements we see are fresh, a continuous fall of pulverized planetary material, the ground-up bones of destroyed worlds, settling onto the corpse of the star that made them. When we read those fingerprints, we are not just detecting pollution, we are performing a chemical autopsy on a dead solar system. And the autopsy can be astonishingly detailed. By measuring exactly which elements pollute a white dwarf's atmosphere and in what proportions, astronomers can reconstruct the composition of the very object being devoured, whether it was a chunk of dry rock or a metal-rich fragment of a planet's core, or, in some breathtaking cases, a body that was rich in water. Scientists have found white dwarfs whose pollution carries the unmistakable chemical signature of water-bearing worlds, meaning that somewhere out there, the shattered remains of wet, potentially once habitable planets are slowly raining down onto the embers of their dead stars. We are reading, in the light of these corpses, the obituaries of other Earths, and in at least a few rare cases, astronomers have even found planets that survived, an intact giant world still orbiting a white dwarf, a lone survivor circling the ember of its dead sun, proof that not every world is consumed, that some endure the death of their star and orbit on through the long cold afterward. It is worth pausing to absorb just how intimate this evidence really is. Because of everything astronomy has shown us about the death of stars, this may be the most personal. When we study a planetary nebula, we are looking at a star's discarded body from the outside, a beautiful shroud light years across. When we caught the flash in the constellation of the Eagle, we glimpsed the act of destruction itself, but from 12,000 light years away, as a single point of brightening with no detail we could resolve. But a polluted white dwarf offers something different and far more specific. It lets us read the actual chemistry of a destroyed planet, to say, with real confidence, this dead star ate a world, and that world was made of these particular elements, in these particular proportions, and it was dry, or it was metal-rich, or it once held water. We are not inferring the death of planets in the abstract. We are taking the chemical fingerprints of specific, individual worlds that have already been destroyed, and reading them off the surfaces of the stars that killed them. Each polluted white dwarf is a death certificate with the cause of death, and the composition of the victim spelled out in the language of light. And that is as close as we will ever come to seeing the Earth's own distant future with our own instruments, because this is precisely what our solar system will look like, ages from now, to any astronomer who happens to study it. Long after the sun has died, long after the Earth has been engulfed or has fallen inward and been torn apart, the white dwarf that was once our sun will sit at the centre of a scattered debris field, the broken survivors of the outer planets, the shattered asteroids, the ground-up remains of worlds. And from time to time, a fragment of that wreckage will spiral in and rain down onto the dead star, and for a while the corpse of the sun will carry, in its thin atmosphere, the faint chemical signature of whatever it just consumed. If, in that unimaginably distant future, some far-off observer turns an instrument toward the cooling ember that used to be our sun, they might detect the trace of iron, of silicon, of oxygen, and they might realize, as we now realize when we look at other dead stars, that this white dwarf is digesting the remains of its own planets. They would be reading, without ever knowing it, the obituary of the Earth, the chemistry of our world, our rock and our metal, and perhaps even the lingering trace of our long-vanished water, written into the atmosphere of the sun's corpse, the last faint signature of a planet that once held the only life anyone knew of. We look at polluted white dwarfs and see the graves of alien Earths. Someday, the Earth's own grave will look exactly the same, and there will be no one left who remembers what was lost. This, then, is the most direct evidence we have of what the death of a star does to its planets. The planetary nebulae show us the body being cast off. The swallowed world in Aquila showed us a planet dying in real time. And the polluted white dwarfs show us the aftermath, the chewed-up remains of entire planetary systems, settling onto the dead stars that destroyed them, their chemistry still legible to anyone who knows how to read it. Across every one of these windows, the message is the same. Stars die, and when they die, they take their worlds with them. Our sun will be no different. One day, far in the future, the white dwarf that was once the sun may carry in its thin atmosphere the faint chemical trace of a destroyed inner planet. And there will be no one left to recognize that the dust raining onto that dead star was once the Earth. Knowing all of this, knowing the body, the act, the aftermath, and the timeline, the question that no one can avoid asking returns with full force. If we know it is coming, can we do anything about it? Could humanity, given enough time, actually save the Earth or save itself? It sounds like fantasy, and yet serious scientists have studied it. In 2001, 3 researchers, Don Korikansky, Gregory Laughlin, and Fred Adams, published a genuine, peer-reviewed paper in a respectable astronomy journal proposing exactly this. Their idea was audacious almost beyond belief. If the problem is that the sun is getting too bright for the Earth's current orbit, then the solution is to move the Earth, to gradually enlarge its orbit, nudging the entire planet outward, away from the warming sun, keeping it always at a comfortable distance as the star brightens. And their proposed method was breathtaking in its scale. You would take a large object from the outer solar system, an asteroid or a comet, perhaps 100 kilometers across, and steer it on a carefully calculated path so that it swings close past the Earth again and again. Each close pass would transfer a tiny bit of orbital energy, tugging the Earth ever so slightly outward, the same gravity assist trick that space agencies use to fling small probes across the solar system, but applied monstrously to an entire planet. The hope behind this is real, the math is striking, and on paper it works. By their calculations, with one carefully aimed flyby every few thousand years, sustained over the remaining life of the sun, you could move the Earth far enough out to keep pace with the brightening and remain habitable for billions of years longer than nature would allow. It is one of the most ambitious ideas anyone has ever seriously proposed. But the danger is just as real, and the authors did not hide it. The margin for error is essentially zero. If a single one of those flybys were miscalculated even slightly, if the great asteroid passed a little too close, it would not nudge the Earth. It would strike it, or come near enough to shatter it, in an impact that would sterilize the planet instantly and undo everything in a heartbeat. You would be playing a game of cosmic billiards with the Earth itself as one of the balls, for billions of years, and you could never afford to miss even once. The very tool meant to save the world could erase it in an afternoon. The scale of the undertaking is almost beyond comprehension, and it is worth dwelling on, because it reveals just how enormous the death of the sun really is as a problem. To move an entire planet, you are fighting against the energy that binds the Earth to its orbit, an amount of energy so vast that all the power humanity has ever generated, across the whole of its history, would be a rounding error against it. The proposed scheme worked around this by being patient, by stealing a tiny sip of orbital energy with each flyby of the great asteroid, and repeating it over and over, with one carefully aimed encounter roughly every 6,000 years, sustained across hundreds of thousands of such encounters over billions of years. It is a plan measured not in human lifetimes, or even in the lifetimes of civilizations, but in the lifetime of the sun itself. No institution humans have ever built has lasted even a few thousand years. This plan would require flawless execution, without a single fatal error, across a span longer than the entire history of complex life on Earth. The patience required is not human patience. It is geological patience, demanded of a species that has existed, in any recognizable form, for only the faintest sliver of the time the plan would take. There are gentler variations on the dream. Rather than moving the whole planet, some have proposed building a vast shade in space, a thin screen, or a swarm of countless small reflectors, positioned between the Earth and the Sun, to block a fraction of the incoming light and hold the planet's temperature steady as the Sun brightens. Such a structure could, in principle, buy time, dimming the lethal Sun just enough to keep the oceans from boiling for a while longer. But it too strains belief in scale, requiring engineering across distances and timeframes far beyond anything we can presently imagine, and it would only delay the inevitable, not prevent it, for the Sun's brightening never stops, and its final swelling cannot be shaded away. Every one of these schemes runs into the same wall in the end. You can fight the Sun's death for a long time, perhaps, with enough ingenuity and enough patience, but you cannot win. The furnace will run out of fuel no matter what shade you build, and when it does, no screen in space will hold back a star that has begun to swell across the solar system. So the verdict on moving the Earth is a strange one. It is not impossible. It violates no law of physics, but it asks for a level of precision, patience, and flawless execution across geological time that strains all belief. Perhaps a civilization vastly more advanced than ours could attempt it. Perhaps the wiser path is the other one, not to save the planet, but to leave it. And that opens the final chapter of humanity's possible responses, the one that turns the death of the Sun from a pure catastrophe into something almost like an opportunity. Because as the Sun dies, for a brief and brilliant window, it does not only destroy, it also opens new doors in the cold and distant places we could never live before. Recall what happens to the outer solar system when the Sun swells into a red giant. The wave of heat that boils the Earth reaches outward and thaws the frozen moons of the giant planets. Scientists at institutions like the Carl Sagan Institute have run simulations of exactly this, asking where in the dying solar system life might find a foothold once the inner worlds are gone. Their answers are tantalizing. Europa, the ice-locked ocean moon of Jupiter, could melt and become a warm, water-rich world, potentially habitable for a window of perhaps 200 million years. Saturn's moon Titan, with its thick atmosphere and its lakes of frozen chemistry, could warm into something startlingly Earth-like, its surface temperatures rising to something a human might find almost pleasant, for hundreds of millions of years. And far out in the frigid dark, the icy worlds of the distant solar system, the realm beyond Neptune, the frozen dwarfs and their cousins, could briefly become temperate real estate. As the inner solar system burns, the outer solar system blooms. The death of the Sun is, for the outer worlds, a brief and unexpected spring. A more advanced dream goes further still. The physicist Freeman Dyson, in 1960, imagined that a sufficiently advanced civilization might learn to capture the entire energy output of its star, surrounding it with a vast swarm of structures to harvest every last photon. Such a civilization, facing the death of its sun, might not flee at all. It might instead wrap the dying giant and feed on its enormous, if temporary, outpouring of energy, riding the red giant phase like a storm to be harnessed rather than survived. And in the deepest future, when the sun has collapsed into a white dwarf, that faint, slowly cooling ember would still glow for an almost endless span of time, and a patient enough civilization could, in principle, huddle close to it, drawing warmth from the corpse of the star for trillions of years, long after the rest of the universe has gone dark. These are speculations, and honest ones. We do not know if any of them are truly achievable, or whether any civilization, ours or another, ever survives long enough to attempt them. But they are not forbidden by physics. They are merely for now, beyond us. What every one of these attempts has in common: the planetary nebulae that show us the end, the swallowed world that previews our doom, the ringing sun that confirms the timeline, the desperate schemes to move or escape the Earth, is that they all circle around a single truth we have been approaching from the very beginning and have not yet fully said out loud. The death of the sun is not a distant horror disconnected from us. It is bound up intimately and inescapably with our own existence, with where we came from, what we are made of, and why there is anyone here at all to fear the ending. And that truth, the deepest one in this entire story, is what we have to face next. To understand the deepest truth about the death of the sun, we have to ask a question that sounds, at first, like it belongs to a different story entirely. Where did you come from? Not your parents, not your ancestors, not the first humans who walked out across the plains of a young world. Go further back than that, much further. Where did the actual material of you come from? The carbon in the long chains of your DNA, the oxygen you are breathing right now, the calcium locked into the architecture of your bones, the iron riding inside your blood that lets it carry that oxygen from your lungs to every living cell. Where were those atoms made? Because they were made somewhere. Every atom in your body has a history that stretches back almost to the beginning of time, and that history is not gentle, and it is not abstract, and it has everything to do with the fate that waits for our sun. The truth is one of the strangest and most beautiful facts that science has ever uncovered. And once you understand it, you can never look at the night sky or at your own hand in quite the same way again. You are made of dead stars, not metaphorically, not poetically. Literally, atom by atom, you are assembled from the ashes of stars that lived and died before the sun was ever born. Here is how we know. When the universe itself began, in the event we call the Big Bang, it produced almost nothing but the two lightest elements. Hydrogen, the simplest atom of all, a single proton with a single electron, and helium, the next simplest, a trace of lithium, and essentially nothing else. That was the entire starting inventory of creation. Hydrogen and helium and a whisper of lithium, and a vast expanding darkness. There was no carbon, there was no oxygen, there was no nitrogen, no iron, no gold, no calcium, no silicon, none of the rich and varied elements that make up planets and oceans and living things. The early universe was a place where none of the ingredients for life yet existed. If the cosmos had stayed that way, there would never have been a single rocky world, a single drop of water, a single living cell, anywhere, ever. The universe began almost completely sterile, holding only the raw fuel and none of the substance. So where did everything else come from? It came from inside stars. A star, as we have seen across this entire story, is a furnace that fuses light elements into heavier ones. Deep in the core of the sun, right now, hydrogen is being welded into helium. And that is only the first step of a process that, in stars across the universe, climbs the ladder of the elements rung by rung. In the cores of stars, helium fuses into carbon. Carbon fuses into oxygen, into neon, into magnesium. In the most massive stars, the fusion races onward, building silicon and sulfur, and at the very end, iron. Every heavy atom you have ever encountered, every element more complex than the two that the Big Bang produced, was forged in the searing heart of a star. The carbon in a pencil, the oxygen in the air, the silicon in the rocks beneath your feet, the gold in a wedding ring, all of it was cooked into existence inside stars, under pressures and temperatures we can barely imagine, over millions and billions of years. The stars are the factories of the elements. They are where the periodic table is written. But forging the elements is only half the story. An element trapped forever inside a star is useless for making planets or people. It has to get out. It has to be returned to space, scattered into the great clouds of gas that drift between the stars, so that it can be gathered up again into new worlds. And this is where death enters the story, because the only way a star surrenders the elements it has built is by dying. When a star dies, it gives back. The most massive stars give back violently, in supernova explosions that blast their enriched guts across light years of space in a single cataclysmic instant. But stars like our sun give back gently, and that gentle giving is exactly what we have been describing throughout this film. Remember the planetary nebula, the glowing shell of gas that a dying sun-like star casts off into the dark. Remember the thermal pulses of the asymptotic giant branch when the swollen star coughs its outer layers into space. Remember the carbon dredged up from the core and carried outward, seeding the galaxy. That is the sun's contribution to the future. When our sun dies, it will not simply vanish. It will exhale almost half of itself back into the galaxy, a vast cloud of hydrogen and helium and carbon and oxygen and nitrogen, the products of 10 billion years of patient fusion, released into the dark to drift and mingle and wait. The death of a star is the seeding of the next generation. It is the universe's way of passing the elements forward. Now follow the loop all the way around, because this is the part that changes everything. If stars must die to release the elements, and if those elements drift into clouds, and if new stars and new planets condense out of those enriched clouds, then our own sun and our own Earth and everything on it must have been built from the ashes of earlier stars. And that is precisely what happened. Roughly 4.5 billion years ago, in an ordinary corner of an ordinary galaxy, a vast cloud of gas and dust began to collapse under its own gravity. That cloud was not pristine. It was not the leftover hydrogen and helium of the early universe. It was enriched, salted through with the carbon and oxygen and iron and silicon and every other heavy element that earlier generations of stars had forged and then released in their deaths. The sun ignited at the center of that collapsing cloud, and around it, from the same enriched material, the planets assembled, including a small rocky world, third from the center, with just enough heavy elements to build a crust and an ocean, and, eventually, us. Every atom of that rocky world heavier than helium was a hand-me-down, a gift, an inheritance from stars that had already lived their lives and died before our sun took its first breath. So consider what that means for the atoms inside you. The carbon in your cells was forged in the core of some ancient star and scattered into space when that star died. The oxygen filling your lungs was built in a stellar furnace that went dark billions of years ago. The iron in your blood, the very iron that makes your blood red and lets it carry life through your body, was created in conditions of almost unimaginable violence, in the cores of massive stars and in the explosions that ended them, and then flung across the galaxy to wait, for ages beyond counting, until a collapsing cloud gathered it up, and a forming Earth claimed it, and life arose to weave it into living tissue. You are not separate from the deaths of stars. You are a product of them. The matter that thinks your thoughts and beats in your chest spent eons inside stars that are long gone, stars whose names no one will ever know, stars that died so that the elements they made could one day become you. Let that sink in. The next time you look up at the night sky and see those points of light, understand that you are looking at the kind of object that made you, and that every one of those stars, in its own time, will die and give its elements forward, just as the stars before our sun gave theirs. Follow a single atom, just one, to feel the full weight of this. Take one atom of carbon in your body, perhaps one that is, at this very moment, part of a strand of the genetic material coiled inside one of your cells, helping to spell out the instructions that make you who you are. That atom did not begin here. Billions of years ago, before the sun existed, before the earth existed, it was assembled in the searing core of some ancient star, fused together out of lighter particles in the slow nuclear alchemy that stars perform. For ages it remained locked inside that star, part of its glowing body, while the star lived out its life. Then the star died, gently, like our sun will, casting off its outer layers, or violently, in an explosion. And that carbon atom was flung out into the cold and the dark, into the vast clouds of gas drifting between the stars. There it waited, for an unimaginable span of time, adrift in the emptiness, until gravity gathered its cloud together and a new star, our sun, began to form. The atom was swept into the disk of debris around the newborn sun, settled into the forming Earth, and became part of the rock of a young planet. From there its journey grew stranger still. It may have spent eons locked in stone, then been breathed out of a volcano into the air, then dissolved into an ancient ocean, then taken up by some early living thing, then passed from creature to creature, from soil to plant to animal and back again, through countless living bodies across the long history of life, until, at last, it arrived in you. That single atom has been on a journey of billions of years, across the death of a star and the birth of a world and the entire history of life, to arrive at this exact moment as part of the living, thinking thing reading these words. And every atom in your body has a story like that one. You are not a single object so much as a temporary gathering of ancient travellers, each with an epic behind it, briefly assembled into the shape of a person. And the journey does not end with you, either. When your atoms are eventually released again, as all atoms are, they will move on, into the soil, the air, other living things, and across spans of time so long that some of them may one day be swept up by the dying sun and scattered into the galaxy, to drift toward the formation of worlds we will never see. You are a way station, not a destination. The matter that makes you is borrowed, ancient, and bound to keep travelling long after you are gone. There is a strange and genuine comfort in that, if you let yourself feel it. Nothing that makes you is ever truly destroyed. It only changes hands, passing from star to cloud to world to life and onward, in a great unbroken relay that has been running since the first stars and will run until the last. The death of the sun, seen from inside this relay, is not an ending of the story of matter. It is simply the moment our particular runner passes the torch forward, into the dark, toward whatever comes next. And here is the turn that makes the death of our sun not merely an ending, but a continuation. When the sun casts off its outer layers in its final act, when it exhales that cloud of carbon and oxygen and nitrogen into the galaxy, those elements will not simply be lost. They will drift, as the elements of earlier stars once drifted, out into the interstellar medium, into the great cold clouds, where new stars are even now being born. And someday, millions of years from now, hundreds of millions, perhaps billions, some of the very atoms that our sun forged across its long life will find themselves swept into a new collapsing cloud, pulled into the heart of a newborn star, or settled onto the surface of a new and forming world. The carbon that our sun made could become the carbon of another biosphere. The oxygen could fill another ocean. The death of our star is the raw material of stars and worlds not yet born. We are the children of dead stars, and our sun, in dying, will become an ancestor in its turn. The same process that made us will, through the sun's death, help to make whatever comes after. This is not the end of a line. It is one turn of a wheel that has been turning since the first stars lit the early darkness, and will keep turning long after we are gone. There is a further layer to this, and it carries us into the deepest future that physics allows us to imagine. We have spoken of the white dwarf that the sun will leave behind, the dense, earth-sized ember of its own dead heart, packed so tightly that a single spoonful of its material would weigh as much as a small mountain. We described it as a corpse, a fading cinder, and in one sense that is exactly what it is. But the story of that corpse does not end when the planetary nebula disperses and the white dwarf is left naked to the dark. Something extraordinary happens to it over the unimaginable spans of time that follow. Something that turns the sun's final remnant into one of the most remarkable objects in all of nature. When the sun first becomes a white dwarf, it will be ferociously hot, the exposed core of a star, glowing white and fierce despite its tiny size. But it will have no fuel left to burn. Fusion will be over. From that moment, the white dwarf can do only one thing. With no internal furnace to replace the heat it radiates away, it will slowly bleed its warmth into space, fading over billions and then trillions of years from brilliant white to yellow to a dull sullen red, growing dimmer and colder with each passing age. And as it cools, something happens inside it that no one would have guessed. The carbon and oxygen that make up the body of the white dwarf, packed together under that crushing pressure, begin to crystallize. The atoms, robbed of heat, settle into an ordered lattice, a regular repeating structure, locking into place like water freezing into ice. Except that this is carbon and oxygen freezing under the weight of an entire star. The dead sun crystallizes from the inside out. It becomes, in the most literal sense the physics permits, a single colossal crystal of carbon and oxygen, an Earth-sized jewel hanging in the dark. People have not been able to resist the obvious comparison, and the comparison is not wrong. The sun's final remnant will be something very much like a diamond the size of a planet. Our star, which gave the Earth its light and its warmth and its very existence, will end its days as a slowly cooling cosmic gem, a frozen monument to the 10 billion years it spent shining. And how long will that take? Here the numbers leave the realm of anything human intuition can hold. For a white dwarf to cool completely, to surrender the last of its heat, and fade into a cold, dark, inert object that astronomers call a black dwarf, would take something on the order of a quadrillion years. A quadrillion, 1,000 trillion years. To grasp how long that is, consider this. The entire universe, from the Big Bang until this very moment, is only about 14 billion years old. The time it would take the sun's corpse to fully cool is not merely longer than the current age of the universe. It is roughly 100,000 times longer than the universe has so far existed. And so here is a fact that genuinely stuns the people who first encounter it. In the entire cosmos, in all the billions of years since the first stars formed, not a single black dwarf has ever come into being. There has not been enough time. The universe is far too young. Every white dwarf that has ever formed, including the most ancient ones, born from the first generations of dying stars, is still out there cooling, still glowing faintly, still on its impossibly slow journey toward a darkness it has not yet reached. The sun's ultimate fate, the cold dark crystal it will finally become, is a destiny that nothing in the universe has yet achieved. Let that sink in. When you imagine the dead, cold, diamond corpse of our sun, you are imagining an object that does not exist anywhere yet, a kind of thing the universe has never been old enough to make. This is not science fiction. The crystallization of white dwarfs is something astronomers have actually observed evidence for in the way that populations of these dead stars pile up at certain temperatures as they release heat during the freezing process, lingering longer than they otherwise would, exactly as the physics of crystallization predicts. The cosmic diamond is not a fantasy. It is the measured, predicted endpoint of stars like our own, and it tells us something profound about the relationship between the sun's death and the deep structure of time itself. The sun will spend roughly 10 billion years as a living, shining star, a span already so vast that all of human history is less than a rounding error within it. But its life as a star will turn out to be the briefest chapter of its existence. Its death will last far, far longer than its life. The fading white dwarf, cooling toward that distant crystalline darkness, will persist for a quadrillion years and beyond, outlasting its own living phase by a factor of 100,000, outlasting the formation of new stars across the galaxy, outlasting very nearly everything. The sun's corpse will still be there, a cold, dark jewel drifting through an emptying universe, long after the last new star anywhere has burned out and the cosmos has entered its final, frozen old age. That deep future has a name among the scientists who study it. We live now in what is called the stelliferous era, the age of stars, the brilliant epoch in which the universe is full of shining suns and the night skies of countless worlds blaze with light. It is the era that made us, and it feels to us like simply the way the universe is. But it is a phase and a temporary one. The stelliferous era will end. Star formation will slow and then cease as the available gas is used up. One by one, across spans of time that dwarf everything we have discussed, the stars of the universe will exhaust their fuel and die. The bright young stars will go first, then the long-lived smaller ones, until at last even the dimmest, most frugal red dwarfs, stars that can shine for trillions of years on a miser's ration of fuel, will gutter and fade. And then the universe will enter what is called the degenerate era, the long cold age of stellar corpses, an epoch populated not by living stars but by their remnants, white dwarfs and neutron stars and black holes drifting through an ever-darkening void. In that era, the cooling corpse of our sun will be one faint cinder among countless others, a frozen diamond among a graveyard of frozen diamonds, all of them slowly surrendering the last of their ancient heat to a darkness that grows more complete with every passing eon. And it is to that fate, in the unimaginably distant end, that the death of the sun finally leads. So let us return, now, to the words of the astronomer who watched a distant star swallow a planet, the words we heard at the very beginning of this story. Kishalay De, looking at the flash of light from a world being devoured 12,000 light-years away, said quietly that we were seeing the future of the Earth. And he was right. That swallowed world is a preview of our own ending, a glimpse across the galaxy of the fate that waits for our planet when our sun begins to die. But now you can hear a second meaning in those words, a deeper one that runs in the opposite direction through time. Because when we look at a dying star, we are not only seeing the future of the Earth, we are also seeing its past. We are seeing the very process that built our world and everything on it. The forging of the elements, the death of the star, the scattering of the ashes from which new worlds are made. The death of stars is why the Earth exists. The death of stars is why you exist. Every dying star we observe, every planetary nebula glowing in the dark, every white dwarf cooling toward its distant crystalline grave, is at once a vision of our future and an echo of our origin. The end and the beginning are the same process, seen from different sides. We are the children of stellar death, and we are bound, in the fullness of time, to become its parents in our turn. There is a temptation, when confronting facts this large, to feel diminished by them, to look at the quadrillion-year fate of the sun, at the graveyard of cold stars waiting at the end of time, and to conclude that nothing we do could possibly matter against a backdrop so vast. But there is another way to read the very same facts, and it may be the truer one. Consider how improbable, how precarious, how astonishingly rare this present moment actually is. We live in the stelliferous era, the age of light, and we happen to live near its beginning, when the universe is still young and bright and busy making stars. We orbit a stable, middle-aged star that has shone steadily for billions of years, and will shine steadily for billions more. Long enough, by an almost suspicious margin, for life to arise, and for that life to become complex enough to look up and ask where it came from. We are made of elements that took generations of stellar death to forge, assembled into a configuration that can wonder about its own origins. Out of the entire history of the cosmos, out of the entire sweep of time from the Big Bang to that final cold darkness, we exist in the narrow, luminous window when all of this is possible. We are not insignificant against the deep time of the sun. We are the impossible fleeting thing that the deep time of the sun made room for, and that reframing changes how we ought to feel about the sun's mortality. A star that lived forever would, in a strange way, give us nothing. It is precisely because stars are born, and shine, and die, that the elements move forward, that planets form, that the chemistry of life becomes possible at all. The sun's mortality is not a flaw in the design of the universe, it is the engine of everything we are. If the first stars had been immortal, locking their forged elements inside themselves for eternity, the universe would still be a sterile place of hydrogen and helium, with no carbon to build a cell, and no oxygen to breathe, and no one anywhere to notice. Death, at the scale of stars, is not the enemy of life, it is the precondition for it. The same process that dooms our distant descendants to flee a swelling sun is the process that gave us a sun to be warmed by in the first place. We are caught inside a cycle of stellar birth and death, and we owe that cycle absolutely everything: our world, our bodies, the light we see by, the very atoms that let us think these thoughts. To resent the sun for being mortal is to resent the only kind of universe that could ever have produced us. This is, in the end, what the death of the sun has to teach, and it is something deeper than fear. For most of this story, we have approached the sun's ending as a catastrophe to be understood and, if possible, survived. The drying of the oceans, the swelling of the red giant, the swallowing of the earth, the long fade into a cold, dark crystal, all of that is real, and all of it deserves the unflinching attention we have given it. But, underneath the catastrophe, lies a continuity that is almost tender. The sun that will one day destroy the earth is the same sun whose ancestors built the earth. The death that waits at the end of our world is the same kind of death that gave rise to it, and the elements that the sun will scatter in its dying are the same elements that will, somewhere, someday, gather again into new worlds and perhaps new life, carrying forward, in their atoms, a lineage that connects the first stars to us and to whatever comes after us, in an unbroken chain of forging and dying and being born again. We are one link in that chain, the sun is another, and the chain itself is older than the earth and will outlast it by spans of time we can name but never truly feel. So when we say that you are made of stardust, we are not offering a comforting metaphor to soften a frightening subject. We are stating the central fact of the entire story, the fact toward which every chapter has been pointing. The death of the sun is not something that will happen to us from the outside, a disaster that arrives like a meteor from the dark. It is woven into what we are. Our origin and our ending are written in the same stellar language, governed by the same physics of fusion and gravity and time, bound together so tightly that you cannot fully understand the one without confronting the other. To know where the sun is going is to know where we came from. To grieve the sun's eventual death is, in some sense, to grieve a member of our own family, the parent star whose light we were born under, whose warmth we have always known, and whose mortality is, in the deepest possible way, our own. There is one more consequence of all this, and it reaches forward into questions that are no longer only about the sun, but about us, about what an intelligent species ought to do when it learns, with certainty, the date of its own world's execution, because we are, as far as we know, the first kind of life on this planet ever to understand any of this. For nearly 4 billion years, life on Earth lived and died beneath the sun without the faintest idea that the sun would change, that it was slowly brightening, that it carried within it a built-in ending for the whole living world. The trilobites did not know. The dinosaurs did not know. For almost the entire history of life, the deadline was invisible, an unread sentence hanging over a world that could not read. And then, in a span of a few short centuries, one species learned to read it. We worked out what the sun is made of, how it shines, how long it has left, and what it will become. We are the first living things on Earth ever to see the ending coming. And that knowledge, terrible as it is also a kind of gift. Because knowing the future, even a future billions of years away, is the first thing any species would need in order to do something about it. The dinosaurs could not have saved themselves from anything, because they could not see what was coming. We can, and what we choose to do with that sight, whether we treat the deep future as someone else's problem, or as the longest and most important project our species could ever undertake, is the question that the death of the sun finally lays at our feet. If we take the death of the sun seriously, not as a curiosity, but as a real event with a real timeline, then we have to confront a set of questions that no human society has ever truly had to face, because no human society before ours has ever known the answers existed. How long do we really have? What, if anything, can be done? And who, if anyone, will be left to do it? These are not idle speculations. They follow directly and unavoidably from the science we have been tracing, and they reshape the way we ought to think about the future. Not the future of next year or next century, but the future measured in the only units the sun respects, which are the millions and the billions of years. The first thing to understand is that the popular image of the sun's deadline is wrong and dangerously comforting. People who know a little astronomy often say that the sun has about 5 billion years left, or that it will not become a red giant for something like 7.5 billion years. And they relax because those numbers are so enormous as to be meaningless. But those numbers describe the death of the sun, not the death of the living world. And the living world dies first, much, much sooner. Recall the slow, relentless brightening we examined earlier, the inexorable increase in the sun's output as it ages. That brightening does not wait for the red giant. It is happening now, and its consequences for the biosphere arrive on a timescale of mere hundreds of millions of years, within something like 600 million years to a billion years. The rising solar output will likely have pushed the Earth past the point where it can sustain the rich, complex life we know, the oceans beginning their long retreat, the carbon that plants depend on dwindling toward collapse, the planet sliding toward a hot, sterilized state long before the sun itself shows any dramatic change. So the real deadline, the one that matters for life, is not 5 billion years away. It is closer to 1 billion, and arguably closer still. That is still an almost incomprehensible span by human standards. But it is 5 times sooner than the comfortable number, and it changes the shape of the problem entirely. And yet a billion years is so far beyond human experience that we have no instinct for it at all, and it is worth pausing to feel just how far beyond us it is. Our species, anatomically modern human beings, has existed for something like 300,000 years. Everything we call history, the first cities, the first writing, the pyramids, every empire that ever rose and fell, every word ever recorded, fits inside the last several thousand years, a sliver so thin that against the lifespan of the sun, it essentially vanishes. The entire age of complex animal life on Earth, going all the way back to the first creatures with hard shells, is only about 500 million years. So when we say the biosphere has perhaps 1 billion years left, we are talking about a span longer than the entire history of animals on this planet so far. to ask what humanity will be doing in 1 billion years is very nearly a meaningless question, because there is almost no chance that anything we would recognize as humanity will still exist by then. Over such spans, species transform beyond recognition or vanish entirely. The honest answer to what will we do when the sun dies is that we, specifically, will almost certainly not be there to do anything at all. Whatever faces the dying sun, if anything does, will be as different from us as we are from the first single cells. But that is not the same as saying it does not matter. And here the assumptions we carry around without examining them start to break down. We move through our lives treating the sun as a fixed and permanent fact, the one thing that can always be relied upon, rising every morning without fail, the very symbol of constancy. And on the timescale of a human life or a human civilization, that assumption is perfectly sound. But step back far enough and something is wrong with our assumptions. The sun is not constant. The sun is not permanent. The sun is a particular kind of object at a particular stage of the process that has a beginning, a middle, and a definite, knowable end. The stability we depend on is real, but it is temporary, a long, calm afternoon between a fiery birth and a fiery death. And once you absorb that, the question of what an intelligent species should do with the knowledge becomes not a fantasy, but a genuine, if distant, practical problem, perhaps the longest-term practical problem, that can be coherently stated. There are, broadly, only 3 kinds of answer, and we have met all of them already in the course of this story. The first is to stay and to engineer, to refuse to surrender the Earth, and instead to reshape the relationship between planet and star. We saw the boldest version of this. The almost unbelievable proposal to physically move the Earth into a wider orbit, nudging it outward over thousands of years to keep pace with the brightening sun and stay within the shrinking band of habitable warmth. We saw the gentler cousins of that idea, the notion of a vast shade hung in space between the Earth and the sun to deflect a fraction of the growing light. These schemes are real proposals by real scientists, and they are not forbidden by the laws of physics, but they demand power, precision, and above all, a continuity of purpose across spans of time that no human institution has ever come close to sustaining. To move a planet is to commit to a project that would outlast every civilization in recorded history many times over, with no room for the kind of lapse that human affairs are endlessly prone to. It is, in the most literal sense, the most ambitious thing a species could attempt. Whether any species could hold itself together long enough to attempt it is another question entirely. The second kind of answer is to leave. If the planet cannot be saved, or if saving it proves harder than abandoning it, then the alternative is to carry life elsewhere, to spread beyond the Earth and beyond the sun entirely, into the wider galaxy, where billions of other stars burn and billions of other worlds wait. This is the dream that has animated so much of our imagining about the future. Ships crossing the immense gulfs between the stars, new worlds settled and reshaped, life seeded across the cosmos so that the death of any single star can never again threaten everything at once. The distances are staggering, far beyond anything our current technology could cross in a human lifetime, and the difficulties are immense. But here, too, the timescales work strangely in our favour. We are not under pressure to leave tomorrow, or in 1,000 years, or even in 1,000,000. If life has hundreds of millions of years before the Earth becomes untenable, then even slow, patient expansion, crossing to the nearest stars over centuries, establishing footholds, then crossing again, could in principle carry our descendants across a meaningful stretch of the galaxy before the sun ever begins to swell. And there is a strange mercy hidden in the sun's death itself, which we have already touched on. During the red giant phase, for a window of a couple of 100 million years, the frozen outer solar system thaws. The icy moons of the giant planets could become temporary havens, warm and watery worlds where life might shelter even as the inner planets burn. The death of the sun does not only close doors. For a brief and brilliant interval, it opens them, offering to anything clever enough to use it a final set of stepping stones outward before the dark. The third kind of answer is the strangest and the hardest to speak about clearly, because it concerns a future so transformed that our words begin to fail. It is the possibility that whatever faces the dying sun will not be biological at all in any sense we would recognize. That intelligence, if it survives across such spans, may have long since changed its substrate, its form, even its definition, into something that can endure conditions and timescales that flesh never could. We saw a hint of this in the most extreme of the survival schemes, the vision of a civilization so advanced that it might wrap a dying star to harvest its energy or huddle for trillions of years against the fading warmth of a white dwarf, drawing out its existence in the cooling dark long after the era of living stars has ended. We do not know if such things are possible. We do not know if any intelligence anywhere ever survives long enough or grows wise enough to attempt them, but they are not ruled out by physics, and across the spans of time we are discussing, what is merely difficult has room to become achievable. The death of the sun, seen this way, is not only a threat but a filter and a challenge. A problem so large that meeting it would require a kind of patience, foresight, and unity of purpose that no human society has yet shown, but that nothing in nature forbids. Lift your eyes from our own sun for a moment, and the problem becomes universal. And that universality is itself one of the most haunting implications of everything we have learned. Every star in the sky faces a version of this ending. Every world that ever hosts life, anywhere in the cosmos, sits beneath a star with a finite life and a built-in expiration date. If there are other civilizations out there, and we do not know whether there are, then every single one of them must eventually confront exactly the dilemma we have been describing. A beloved, life-giving star that is also inescapably a slow-burning fuse. The death of stars is not our private misfortune. It is a deadline written into the basic physics of the universe, faced by every form of life that ever arises anywhere. Some have wondered whether this very fact might be part of why the night sky seems so silent. Whether the leap from a single fragile world to a future spread safely among the stars is simply too hard, and most life never makes it, flaring up and dying out on its home planet long before it could ever escape. Or perhaps the opposite is true, and somewhere out in the dark there are ancient civilizations who solved this problem ages ago, tending their dying stars, moving their worlds, riding out the deaths of suns with a competence we can barely imagine. We cannot know. But the death of the sun reframes the entire question of life in the universe, because it tells us that for everyone, everywhere, the clock is always running. And that brings us back, finally and humblingly, to the present. Because there is a danger in all of this deep-time grandeur, a way that contemplating billions of years can become a kind of escape from the years immediately in front of us. It would be a strange and bitter irony if a species that worked out the entire future of its star, that mapped the red giant phase and the helium flash and the cooling of the white dwarf across a quadrillion years, could not manage to survive the next few centuries of its own making. The sun is generous with time. It offers us hundreds of millions of years, a span so vast it borders on the infinite from a human point of view. But that generosity means nothing if we squander it. If we extinguish ourselves or wreck the only world we have, long before the sun ever lifts a finger against us. The deep future the sun grants us is not a guarantee. It is an opportunity, and opportunities can be wasted. The most sobering implication of the sun's death may be this, that the greatest threat to humanity's long future is almost certainly not the sun at all, which will leave us alone for ages yet, but ourselves, here and now, in the narrow window we actually inhabit. The sun has given us 1 billion years. The question is whether we can give ourselves the next 100. There is a further dimension to all of this, quieter than the engineering schemes and the dreams of starships, but in its own way just as demanding. It concerns how a species ought to think and feel when it knows, with real confidence, the eventual fate of its world. For all of recorded history, human beings have lived as though the stage we perform upon were permanent, the ground solid, the sky fixed, the sun an eternal given. Our institutions, our plans, our very sense of what counts as the long term, are built for spans of years and decades, occasionally centuries. A government that plans a generation ahead is considered visionary. A project that takes 100 years to complete is considered nearly superhuman in its patience. And yet the death of the sun, asks us to hold in mind a horizon millions of times longer than anything our politics or our economics has ever seriously contemplated. It asks whether we are capable of caring, in any practical way, about descendants so distant they will not be human, living in a world we will never see, facing a crisis we will never share. This is a moral question disguised as an astronomical one. It is the question of whether the chain of generations is a thing we hold ourselves responsible to, or whether each age simply consumes what it finds and leaves the future to fend for itself. The sun's slow brightening does not care how we answer. But the answer says a great deal about what kind of species we choose to be. And this, perhaps, is the deepest reason that a distant star swallowing a distant planet deserves to be called a preview, and not merely a curiosity. When that flash of light reached our telescopes from 12,000 light-years away, it did more than confirm a theory. It collapsed the distance between us and our own ending. For most of history, the death of the sun was an abstraction, a line in a textbook, a number so large it could be safely ignored. But to watch it happen, to see a real star, somewhere out in the galaxy, do to a real planet exactly what our sun will one day do to the Earth, is to be handed a mirror held up to the future. It turns the abstract into the concrete, the theoretical into the witnessed. We are the first generation of human beings ever to look through a telescope and see, with our own instruments, a working model of the last day of our world. That is an extraordinary thing to be alive for. It is frightening, and it is humbling, and it is also, in a strange way, a privilege. To live in the brief moment when a species first becomes able to see its own deep future, clearly enough to be moved by it. What we do with that sight is up to us, but we cannot any longer claim that we did not know. Let us go back one last time to where we began, to that single point of light that flared in the darkness to 12,000 light-years away, in the constellation of the Eagle, and faded again. A star, an ordinary star not so very different from our own, brightening suddenly as it drew a planet down into itself and swallowed it whole. For a few days, that distant furnace blazed with the light of a world ending, and then it dimmed, and the planet was gone, folded into the body of its star as though it had never been. We opened this story with that image because it is the closest thing we have ever seen to a photograph of our own future. Somewhere in that flash was the Earth. Not our Earth, not yet, but the Earth as it will one day be, when our own sun reaches the end of its long life and turns at last upon the worlds it once warmed. We have spent this entire journey trying to understand what that flash truly means, and now at the end we can finally hold the whole of it in view. Think of the full arc of the sun's life, all of it at once, compressed into a single sweep of the imagination. It began as nothing but a cold, dark cloud of gas and dust, drifting in the spiral arm of a galaxy, salted with the ashes of stars that had already died. Gravity gathered that cloud, pulled it inward, squeezed it until its heart caught fire, and a new star blazed into being. Our sun, newborn, surrounded by a disk of debris from which the planets, including ours, would slowly assemble. For billions of years, the sun has shone with a steadiness so reliable that the life beneath it could afford to forget the sun was even there, taking its light and its warmth as simply the background condition of existence. That steadiness is the gift we were born into. But it is not the whole story, and it was never going to last. Slowly, imperceptibly, the sun has been brightening all along, and one distant day that brightening will tip the earth past saving, the oceans retreating, the air growing thick and hot, the living world drying to silence beneath a sun grown too fierce to bear. Then, ages later still, the core will falter, the great thermostat will break, and the sun will swell into a red giant vast enough to swallow the inner planets, a bloated crimson titan filling the sky of a scorched and dying earth. There will be a final convulsion of fusion, the helium flash hidden deep in the core. There will be the long pulsing exhalations of the dying star, casting its outer layers into space as a glowing nebula, beautiful and brief. And at the center of that fading cloud, the sun's true corpse will be left behind, a white-hot ember the size of the earth, cooling across spans of time so vast that the universe is not yet old enough to have produced even one of them, crystallizing at last into a cold, dark diamond drifting through an emptying cosmos. That is the life of our star, From the first spark to the final cinder, that is the whole of it. And we are here, for this brief and luminous middle chapter, alive beneath the steady sun. It is worth pausing on how extraordinary that is. Of all the moments in the sun's immense biography, the cold cloud before it, the swollen red giant to come, the quadrillion-year graveyard at the end, we exist in the narrow, bright, hospitable window when the sun is calm and the earth is warm and life is possible. We did not choose this moment, and we did nothing to earn it, but we are the ones who happen to be standing in the light. For as long as there have been human beings, the sun has been the central fact of existence, the bringer of day, source of warmth, the measure of the seasons, the thing without which there would simply be nothing at all. Across every culture and every age, people have watched it rise and set and ordered their entire lives around it, and they were right to, because everything they were and everything they had came, ultimately, from that single star. We are no different. The food we eat is sunlight, captured by plants and passed along. The energy that runs our world is, in the end, almost all of it stored sunlight in one form or another. The very atoms of our bodies were forged in stars like the sun and scattered by their deaths. We are, in the most complete sense imaginable, creatures of the sun, born from the kind of process that made it, sustained every single day by its light, and bound to it by a kinship deeper than we usually allow ourselves to feel. That is what makes the knowledge of the sun's death so strange to carry. It is not the cold, impersonal extinction of a distant object. It is the eventual death of the thing that gives us everything, the slow mortality of our own parent star. And we are the first beings on this world ever to know it is coming. For nearly 4 billion years, life flourished and perished beneath the sun in complete ignorance of the sun's fate, never suspecting that the source of all its warmth carried within it the seed of an ending. We are the ones who finally read the sentence written in the sun's own light, who measured its composition, weighed its fuel, traced its future across billions of years, and understood, at last, both where it came from and where it is going. That knowledge is a heavy thing, but it is also, perhaps, the most human thing we have ever done. To look at the source of your own existence, to see clearly that it will not last forever, and to keep looking anyway, without flinching, trying to understand. That is what our species does at its best. We are the part of the universe that has learned to contemplate its own origins and its own ending. We are the sun's matter, organized in such a way that it can look back at the sun and comprehend the whole of its life and death. There may be nothing else like us within reach across the whole vast dark, and here we are, doing exactly that. So, what are we to do with this knowledge? This sentence we have learned to read, this preview we have been shown. We could let it crush us. We could decide that an ending billions of years away drains all meaning from everything we do, that against the cold arithmetic of deep time nothing matters, and turn away. But that would be a misreading of the very story we have just told. Because the death of the sun is not only an ending, it is, as we have seen, a beginning wearing the mask of an ending. The same process that will one day destroy the earth is the process that built it. The same stellar deaths that lie in our future also lie in our past. And the elements the dying sun will scatter are the same elements from which new worlds, and perhaps new life, will someday be made. We are not standing at the edge of a meaningless void. We are standing in the middle of a vast, turning cycle of creation and destruction and renewal that has been running since the first stars lit the darkness, and will keep running long after our sun is cold. The death of the sun is one beat in that endless rhythm, and we briefly, miraculously, are here to witness it, to understand it, and if we choose, and if we last, to do something about it. For we are not entirely helpless before this future, and that may be the most remarkable discovery of all. We have imagined moving the very Earth to a safer orbit. We have imagined shading it from the swelling sun, or carrying life outward to the thawing moons of the giant planets, or crossing the immense dark to other stars, or enduring in forms we cannot yet picture beside the cooling ember at the end. None of these may come to pass. All of them may prove beyond us, or beyond whatever comes after us. But the fact that they can even be imagined, that they are not forbidden by the laws of nature, but only by the limits of our present power, means that the death of the sun is not necessarily the death of everything the sun gave rise to. A species that knows its star will die, and that begins, even faintly, even now, to think across the spans of time such knowledge demands, has already done something no other life on this world ever managed. It has lifted its eyes past its own brief moment and taken responsibility, however tentatively, for the deep future. Whether we ever follow that thought through to action, no one alive can say, but the thought itself is the first step, and we are the first ones ever to take it. And so the death of the sun, in the end, is not really a story about destruction at all. It is a story about belonging. It tells us that we are not visitors in this universe, dropped in from somewhere outside it, but native to it, woven from its oldest material, kin to the stars in the most literal way there is. It tells us that the light we are warmed by came at the price of countless stellar deaths, and that our own star's death will pay that same price forward, into a future we will never see. It tells us that everything that lives is borrowed from the deaths of stars, and will, in time, be returned, to be borrowed again. We are away for the matter of dead stars to wake up briefly and look around and understand where it has been and where it is going, and then to lie back down and be folded again into the great slow turning of the cosmos, from which new wakings will someday arise. The sun will die. The earth, most likely, will die with it. But the story does not end there, because in this universe nothing truly ends. It only changes form and moves on. The atoms remember. The cycle continues, and somewhere, ages hence, in the light of a star not yet born, gathered from the ashes of suns not yet dead, something may once again open its eyes and wonder at the sky. The next time you step outside on a clear day and feel the warmth of the sun on your face, let yourself feel the whole of it for just a moment. That warmth has crossed 93 million miles of empty space to reach you. It was made in a furnace at the heart of a star by the same nuclear fire that has burned for 4.5 billion years and will burn for billions more. It is the same light that fell on the first living things and on everyone who has ever lived. And it is the light of a star that is, even now, slowly and imperceptibly climbing toward its death. We live in the long afternoon of the sun, past the bright morning of its birth, not yet near the red and terrible evening of its end, in the calm and golden middle of its day. It is a good time to be alive. It may be the best time there will ever be. And we are here for it, made of stardust, warmed by a dying star, the universe briefly awake and looking up. That is not a tragedy. That is a gift almost too large to hold. The sun will die, but it has not died yet. And under its steady, ancient, borrowed light, we are still here, for now, for this long, bright moment, alive beneath a star that made us, and that we have only just begun to understand.